talk about where we're going from here. Now, here we go. Before we get started here, let's go over a few kind of end of the term type situations. Number one, okay, I should have been saying this all along. I think I've mentioned it a time or two, but let me say it every time from now on. Have you done the student course evaluations yet? Okay, please do the student course evaluations. Okay, they don't have to be done immediately, but don't forget them. It's so easy at the end of the term with finals and everything else for things to pile up and then just blow them off. So please remember to do the student course evaluations. I particularly want to see what. Now, let me make something clear in case you don't understand this. I will never see what you say on your evaluation. All I see is a composite. In fact, they don't let me see anything until a certain number of students have done it, and then all I see is the composite. So there's no way an instructor will ever know what you said about a class. What we need to know is what the class is saying about the class, okay? So please do those. They also usually ask you to do one or two additional ones, like, you know, registration process or library or something like that, maintenance or something. Do those too, because whereas we get feedback every time we see you, some type of feedback, positive, negative, or otherwise, those folks, that's the only feedback they get. So please do these student course evaluations. Okay. Sooner rather than later, but just don't forget by the end of the term to do it. Now, let's talk about where we are now and where we're headed. We're in Chapter 6. We're in 6.4. We're starting it today. And then we've got 6.5, 6.6, and these are pretty short sections. And that's it for the Chapter 6. I think we'll finish Chapter 6 fairly easily today. We'll get started in Chapter 8. We probably won't get too far in Chapter 8. Okay? Then we have the lab, the last lab in Chapter 6, the electromagnetism lab. We'll be doing that. Now, we'll probably start it in 253 if it's available. If not, 255 will be fine. But basically, there are also going to be some walking around the halls. One place we've got to go to also complete that lab. We'll go down to the records area and complete that lab there, or that's part of the lab. We'll come back and wrap up back in the lab. But whichever lab we wind up, it really doesn't matter. Okay, so that's today. That means next Tuesday we will be continuing Chapter 8. Now, Chapter 8 is a fairly long chapter, so we may, the odds are we're not going to, well, we may finish Chapter 8 or may not. But anyway, we'll have the test on Chapter 6 next Tuesday. Okay. So don't forget that. Have your formula equation sheet ready for that. It's next Tuesday. Then Thursday is the last day. Okay. Tuesday is the last day of class, and Thursday is your final exam. Okay. Now let's talk a little bit about that. I think Wesley or someone was asking earlier, when are you going to get your other stuff back? All of it's coming back to you next Tuesday, which means everything has to be turned in by next Tuesday. Because next Tuesday it's all going back. I can't accept anything after that, except maybe the research papers. Tuesday is the last day to turn in the research paper. After Tuesday, you start losing points. You can turn it in late, but you'll be losing points. Your other stuff, your labs and your tests, Tuesday is the last day to turn them in, because those are going back to you. I can't return your research papers to you because periodically they ask for samples of student writing. So I have to hang on to those. But your others, labs and tests, are going back on Tuesday, which means they've got to all be in by Tuesday. Okay, you can turn them in Tuesday, you just won't get them back Tuesday, but I can't accept anything after I turn those back. Is that understood? Okay, so that's labs and tests. So that means today and Thursday, you better make sure you get them all and you complete them all or have them ready to turn in that next Tuesday. Okay. Now, So that's Tuesday. I return all your stuff to you. We finish chapter 8. And if we finish chapter 8, we'll have the lab on chapter 8 also on Tuesday. I think we'll probably be pretty good in line to do that. Yes?
How long ago final going to be?
It's really short.
Really short?
Yeah.
Can I go ahead and get that test off this Thursday and take it right now?
Well, we're having class right
I
now.
was going to multitask.
What's that?
I was going to multitask.
I can't hear.
I was going to multitask.
Oh, I see. Okay. But you have to go early?
That is early.
You do? Okay, you have to go early too? Okay, so anyone, you have to go early too? Huh?
My mother is having surgery today.
I'm sorry to hear that. Okay. So you're out to, did you do the test Thursday? You did. Okay. How about Kelvin? Were you here Thursday? Did you do the test Thursday? Okay, you did. Okay. Well, we'll have at least one person if Zaria comes back. Okay, are y'all going to do it in the room or do I need to send you somewhere else? Okay. Well, since I'm breaking to do this, let me go on and what else do you need?
The lab for Thursday, the lab for today, and the test the lab for Thursday.
Okay, say that one more time.
The lab and test from last Thursday, the lab for today, and do we have a test Thursday? This Thursday coming up?
Yeah.
I need that too.
I don't have that one off yet. Okay. Okay, well, you'll have to come in sometime and make that up. So, two of you, before class, I gave you lab for Thursday, right?
Yes, sir.
Okay. So, you need the lab for Thursday. Didn't get deep enough. May still not be deep enough. Oh. And how many of you need the test?
3.
3? Okay. And 1 needs the lab. Okay. All right. So I think we got up to next Tuesday. Okay. Thursday of next week is final exam day. So that's when we have the final exam is 1 page, matching, not multiple choice. It's going to be pretty straightforward. Okay. Now, since that's all we're going to be doing on Thursday, wait. If we don't finish chapter 8 until Tuesday, then its test will also be Thursday. That'll be like a regular test. So it's probably 30 minutes worth. The final, I doubt if it's going to be much more than 15. And since that's all we'll have left on that Thursday, what do y'all think about pizza on Thursday?
Next Thursday?
Yeah, next Thursday. Not this coming Thursday, the following Thursday, the final exam day. That be okay? Or is it too late to eat on 1:15? Is that okay? Okay. So we'll probably plan to have pizza, and then we'll have the test on Thursday. Okay? That's going to pretty much wrap up the term. Now, technically, they say that your exam's supposed to be Monday, the following Monday, whatever that is, the 6th. But I think what is going on here, y'all have your schedules to be here in class on Tuesdays and Thursdays. You know, some people probably can't come on Monday. And then if everybody has their test, the second mini-term test on Monday, that means you all are have class on the same time, same day, and everything. That's sort of nuts. And are any of you graduating this term? Nobody? None? Wesley? No. Okay. No graduation this term. If you were, your grades have to be in, but none of you are. Those grades have to be in noon on Friday. So how can I give the exam Monday? Okay, I have to have your grades in on Friday. So we're going to have our test then on Thursday. Okay. Now, any questions about how we wrap up the term? So let's hit Chapter 6, Electricity, 6.4, Electric Currents and Magnetism. Now, I think I've said this a couple of times already, and I'm going to say it probably several more times. What produces a magnetic field is a moving charge. Even in that little magnet, your compass, or whatever it is, that refrigerator on your magnet, what creates the magnetic field is a moving charge. And a moving charge, of course, is a current. Charges in motion is a current. That's what produces a magnetic field. Okay? It always does, it always will. Now, charges are always moving. Electrons are always going around nuclei. So why aren't every material magnetic? Well, because you have one electron going this way, one going that way, so all the magnetic fields cancel each other out. Except for three metals. What are they? And three metals have permanent magnetic fields. Iron. Second. Not copper. Second. Nickel. And cobalt. Cobalt. Okay? All right. So iron, nickel, and cobalt. Those are the only three materials, and there's just something about their atomic and electron structure that they have a moving charge around one axis more than other axes, and that's what creates that. But even within iron, nickel, and cobalt, you can have domains that are, the fields are going all sorts of ways, and they cancel each other out. It's only occasionally do you create that. So moving charges create magnetic fields. So if you have a wire, what kind of current must be going through that wire to produce a magnetic field? AC or DC? DC only, because AC would be doing like this, so the field would be doing like this, and you have no field, okay? But with AC, magnetic, with a charge going in one direction, how? Again, we have this issue with what the charge is and which way it's going. If you count conventional current, take your right hand, point your thumb in the direction that conventional current would be flowing, and then your fingers on your right hand will wrap around in the direction of the magnetic field. If you do it with the electron flow, then you have to use the left hand, okay? But most of the time, we'll use right-hand rule, okay? And basically what it is, if you were to put a compass, so a wire with a pretty strong DC current flowing through it, and you sprinkled iron filings on here, or put a compass, you would find that the compass needle points in this direction, and that would be the direction of your magnetic field. Around a circular path, around the flow of the current. Make sense? Anytime you have a moving charge, which is a current, you have an induced magnetic field. Now, they're missing a slide here, it looks like. The shape of the field is determined by the geometry of the current. Now, in the last one we saw, if you have a straight wire with a current flowing in one direction, then you have basically concentric circular field lines. All right, thank you. Circular field lines. No, I put that in the wrong place. Okay. All right. Now, other configurations will determine. What if you have a current loop? So instead of one single wire, straight wire, concentric circles, what if you have a single current loop? Well, let's take a look at what's happening with that. Okay, if the electron current is this way, that means the conventional current is in this direction, and then all along that, notice your right-hand fingers are pointing up toward the center of the thing. That means the north pole, you might say, of that loop would be up, south pole down. The other thing this does for you, making a single loop, is strengthens the field, because all these magnetic field lines are adding to each other. Okay? If you just had one straight wire here, you just have the concentric circles around it. But as it is now, you have all these are adding up, so it makes a stronger field to have a current loop. What if you have a bunch of current loops? Now, some of you are in electronic type stuff, right? Okay? What do we call a bunch of a coil of wire through which a DC current is flowing?
Magnetic field.
Okay, it produces a magnetic field. What do we call that coil of wire? Solenoid. Is that right? That's basically what a solenoid is. What you've got is not just one loop of wire, but a bunch of loops in the same direction, and now all these magnetic fields are adding and adding and adding to each other, and that's exactly what you got in a solenoid. Okay? Now, the one we just had is this single wire. Let me go back and show it. Okay? Whoops, wrong direction. That way. Okay? Here it is, but I'm going to take out the magnetic field lines, which again are going like this, okay, because its directions are conventional. So that would be the little circular fields would be pointing up in the center of that loop, and that creates the north pole in this direction, the south pole in that direction. The single loop of wire through which a direct current flows will produce a magnetic field. Stronger than if it was one straight wire, that one loop. Do many loops, and that gives you something like a solenoid, like right here. Here we have the, okay, and again they show the electron current. If you did it in the direction of the conventional current, then your fingers in the right hand are always pointing into the loop here. You have a very strong north pole there, a very strong south pole there. Because look at all the concentration of your field lines here and your field lines there. The interior, very strong field lines, exterior, much weaker. What does that look like? That just looks like a bar magnet with the north pole in that direction, south pole this way. It looks exactly. In fact, if you'll get that image in your brain, okay, I'm going to fly through some slides back here. Whoops, went too far. Ah, there it is. Doesn't that look a lot like a bar magnet? The north leaving there, pointing upward, and coming in the south. Isn't that just like that? I only turn sideways. Just like a bar magnet. Difference being, open the switch, the magnetic field disappears. Close the switch, it comes back again. Okay? Isn't that what a solenoid does? Okay? You have some sort of controller there, opens the switch, no field, close the switch, strong field. So that's what's going on in a solenoid. Okay? Now, we're going to do something else to that. Basically, that coil of wire that we have there, strong magnetic field, what we're going to do is put in a ferromagnetic core. What do we mean ferromagnetic again? What three metals must be included? Well, at least one of them? Iron, nickel, or cobalt. Exactly. If you have any of those or alloys of those in that core, now you have not just a field induced by the coil of wire, but you have a core that enhances that field, okay, or reacts with that field. The current carrying wire is wrapped around that core, And now you have a field enhanced by the combination of the coils of wire, basically your solenoid, with the ferromagnetic core. And again, the magic on this, and here's Rhodesia. Here. Okay. Just like the solenoid, this can be turned on and off. Now, guess what? This electromagnet, those wires wrapped around it, more turns you have, stronger and stronger the field. You can up the current as much as you can get away with, and that can be, get this, many times stronger than your strongest permanent magnet. Electromagnets can be way stronger than permanent magnets. But the beauty of them is they can be turned on and off. Now, I don't know if you've ever been, never been out of the Mobile to see this, but I know it happens in just about every big shipping port that we have, where these big container ships come in. And basically how they do things these days, they haul these containers as the trailer on a truck, right? The containers are fixed on the chassis of the truck. They can be released, and they're made out of metal, iron, nickel, or cobalt, guaranteed mostly iron. And so they are magnetic, and rather than in the old days, they had the stevedores, or whatever you would call them. They would have to bring in the stuff, they'd have them in pallets, they'd have to hook them to the pallets, make sure they had it balanced and all like this, pick them up with a crane, lower them onto the ship, and then another team up there had to unhook them and make sure that all goes back. That took a lot of time, and it was really risky. What do they do today? They put an electromagnet, lower it down, unhook it from the chassis of the truck, turn on the juice, picks it up, moves it to the ship, lowers it onto the deck, turn off the current, it drops it and goes back and gets the next one. You don't need cabling, you don't need ties, you don't need anything else, you don't need a team up here and a team down there, you just move it. One operator, basically, you got to have a few people. Much, much more efficient, okay? And really easy to do. It's used in many applications, that's one, but every meter that you have is using electromagnets. Switches use electromagnets. Speakers use electromagnets. Motors, engines, everything uses electromagnets. Just all over the place, okay? So let's look at the meters first, okay? Now these are instruments for measuring, this one happens to be measuring current, the ammeter. And in your lab last Thursday, those of you who were here to do it, we were using digital ammeters. But these are based on the same type deal, okay? Now what you have here is a coil of wire, and you have a spring mechanism in here. And as your current increases, this is housed inside a big permanent magnet, okay? North pole here, south pole here, your field is pointing in this direction. Strong magnetic field is there permanently, okay? Now, you turn on the juice in your coil, and I don't know which way, it's hard to tell which way this is going, but let's just say it's this way, and this may be where it's pointing. Turn on the juice, and now this may become a stronger north pole, so it gets repelled by this north pole and attracted by the south pole. And the more juice you put, the greater the current that you put in, the stronger the reaction is. Well, the stronger the reaction, it's going to move up here. You have this calibrated for the different currents that would take it to move that, and there you have an ammeter. Okay? Now we do have in the lab some analog ammeters that do exactly this. You can't see all that inner stuff, but you know it's got to be there. Okay? So this is what? It uses a magnetic field produced by the current. The more current you have, the stronger the field, the more it's moved. Okay? That's what you're measuring. Okay, the magnetic field, and hence the deflection is proportional to the current, so therefore you have this calibrated for different currents, and you can tell what your current is in any unknown one. Okay? Now you can modify this to be measuring potential, because guess what? The resistance in this coil is the same now as it would be for a voltmeter. The thing is, if you increase the voltage at the same resistance, you're increasing the current at the same resistance. So this could be calibrated for volts. Same setup. Okay? Voltmeter or ammeter. Now the difference comes when it's an ohm meter, because the ohm meter is in reverse. So this would be a large resistance here, smaller resistance as you go this way. So unless you do a switch in the current flow, then you'd have to calibrate for ohm meters in the opposite direction, because that's in inverse proportionality. But there's your electric meters. Whatever electric meter you have. Now, most of you nowadays, I'm guessing just about all of you use digital, right? But you know, this is what's going on inside the digital too. You've got the same kind of setup, okay? But not just meters, switches do the same thing. This is a typical switch that's in the old kind of thermostats. Now, I can't look into these new ones. They may be some sort of a digital setup as well. But in the old thermostats, I wouldn't be surprised if the same thing is happening here. You have your bimetallic coil here, and the more it heats up, the more it expands. And let's see, as it expands, it's forcing this vial to go this way. If it tips it enough, then that connects to a current, and a small current relay circuit, that's why they talk about relays here, it connects here, and that small current hits an electromagnet, greatly increasing the magnetism. The magnetism increase now pulls on is attracted to this metallic strip here that has iron, nickel, or cobalt, is attracted to that, pulling on the spring. When it makes contact, then it turns on your heat pump. And that's how a thermostat works. Boy, it's having trouble these days. Last night we had to have the heat on. Today we're going to have the air conditioning on. So it's really working overtime. Well, if anyone was home, my wife would have it on. I wouldn't. But anyway, the heat pump, if it goes one way, heat comes on. The other way, air conditioning goes on. This is how it works. Of course, you probably have to set it and tell it which one to go. Okay? So it uses a low voltage control circuit here, very low voltage, to switch a larger circuit, your heat pump, the compressor there. First step in refrigerate to our air conditioner is compressing a gas and a refrigerant, and that's what this is doing. You're going to need a large current to do that. So a very small current here, the relay activating a much bigger current to make it comes on. To switch a larger high voltage current on and off. The mercury switch in the thermostat determines that, because mercury is a liquid. If it tilts too much, it's going to connect the switch. Mercury is electrically conducting, but it's not magnetic. Okay, so it has nothing to do with the magnet. It just turns on the switch. Now, similarly, solenoid switches. I don't think they have a slide for that. No, they don't. Works almost the same way. A movable, spring-loaded, just a lot like this, iron core, and this is your iron core here, okay, responds to a solenoid field, and a solenoid field would be just like this, only not an iron core, it would be a solenoid field, and then it responds. So water valves, when you get too dry, it pulls and turns on the sprinkler system. Auto starters, when you turn the switch, then that activates the starter motor, okay? VCR switches. All you're doing, and what you're doing with punching buttons now, is basically adjusting the electronics, okay? You're adjusting the electrical fields and therefore the magnetic fields. VCR switches, activation bells and buzzers, whatever, those are all done using electromagnetic switches. Just about all of them, okay? Now, most of our sound technology. Now, I can't tell you what sound technology your cell phones use. I don't know if anyone actually knows for sure. I know some people do, but in general, they're proprietary and they probably don't let that go out a lot. But in the old style telephone or speakers or anything else that you have, basically what's going on there, let's just imagine the telephone. The old handheld telephone set. Y'all don't even remember those, do you? You're too young to. No, Grandma had one, didn't she? Okay, yeah, okay. You've seen them before. What happens, remember that little thing at the bottom that has little holes in it? Well, when you speak in that, little air pulses, when you speak, hold your hand in front of your mouth when you're speaking, and you can feel little air pulses. Vibrations, compressions and rarefactions of your waves, the sound waves, okay? So when it vibrates, it's pushing together carbon granules, changing the resistance of them. Carbon, being a pretty good electrical conductor, when you press them together, now they have less resistance than when they were further apart. When the rarefaction, which is when you don't have a pulse going and they pull apart, then they have more resistance. So the change in resistance varies the current because it's a constant voltage across there. A change in resistance changes your current. Well, that changing current then is changing in electromagnet. Okay? So, we'll see a picture of that. Let's see if we got it now. Yeah, here's the old guy. See, he's the grandfather. Okay, good deal. Were you able to call in all the answers you needed? Okay, never mind. Okay. Huh?
That's how I was.
Oh, sorry about that. No, I'm not. Okay. All right. Now, as he's talking into this old cell phone, okay, you remember this. The sound waves go in. Here's the compressions and the rarefaction. They call them condensations. They condense the air molecules and then they spread them out, condense them, spread them out. That's why they call them condensations. It's not like water collecting on glass, but it's compressions and rarefactions. Same type deal. So when they compress, they force the granules together. Less resistance, more current flows through because it's a constant voltage across there. More current goes through, you send the signal through the wire. Okay? Now, on the other end, let's see if they show that. Yeah, on the other end, the wire sends that, and this is to the hearing part, the part against his ear, sends a bigger current through there, and the bigger current is then going to the electromagnet here. Why they have a space here, I'm not sure. The electromagnet here send more current. It's probably going to pull it, okay, closer together. And if it does that, your paper cone gets moved. So at the other end, the same current that is created here, varying current here, varies here, but now it's sending out a signal, and you can hear it. Now, what's amazing to me is that you hear not just noise, but you hear actually enough of a discrimination between tones and things like this that most people, you pick it up and you know who's talking to you. People with very similar voice quality, you may have trouble distinguishing that, but basically, I mean, my wife knows her mom's voice over the phone. How in the world can the phone give you that kind of quality? And yet it does, okay? So in the speaker, the varying current changes the field of the electromagnet, moving the permanent magnet up and back. That permanent magnet coming up and back, okay, it then presses on the paper field or retracts from the paper field, one or the other, which then sends these same condensations or are compressions and rarefactions here, and that same signal that came in here is coming out here. Perfectly, to me, amazing. And Alexander Graham Bell, I guess, is largely responsible for developing this. Okay? The moving magnet vibrates a spring attached to the paper cone, producing the sound, and that sound is so similar in quality to the sound that went in, most people can recognize voices and things like that over the phone. Now, bad connections, yeah, you're not going to be able to do it, but, you know, most of the time, I have such a bad hearing loss, and at certain frequencies are worse than others. Unfortunately, my father-in-law, that's his frequency. So when he calls on the phone, I can hardly understand what he says. But I know when I pick that up and I can hardly hear him, it must be him, because his frequency is just the frequency that I have trouble hearing. So I say, oh yeah, I act like I understand every word he says. Okay. So here's another application of electromagnets, electric motors. What's happening in an electric motor? Well, these convert electrical energy to mechanical energy. That's why it's a motor. You plug in the motor, pull the switch, and now it starts turning what? It could be your electric lawnmower. It could be your weed eater. If it's run electrically, you're changing electrical energy into mechanical energy. Well, here's how it works. There's two working parts. One works and one just sits there. The sitting there part is the field magnet. Again, strong north pole here, strong south pole here. For some reason, they drew them backwards from what they had before. Doesn't really matter. The field lines are going this way, from the north to the south. Remember that? Field lines going in that direction. Okay, the armature is the thing that's free to turn. It's a movable electromagnet. It's an iron core, or ferromagnetic core, with the wires wrapped around it. Okay? Now, it has brushes here, and these have basically a split ring type thing to it, that when the brushes are touching anything along half of that turn, and this, by the way, is called a commutator, a split ring commutator. And when they're touching anywhere along this half of the turn, the current's flowing in one direction and then leaving in the other direction. Okay? So what happens is if you turn on the juice, the current, and the current then is wrapped around in such a way making this a north magnet, that's repelled by this north magnet and turns this on its axis here, turns it so it's attracted to the south. The south here is repelled from the south, attracted to the north. Because remember, like poles repel, unlike poles attract. So that moves it halfway, well, a little over halfway, and as it gets turning here, if the south continued, it's going to get right in line with that north and hang up right there. Not move. Okay? So you went and got her, huh? Okay, good. Okay. Good for you. Okay. All right. We're talking about electric motors here and how electromagnets are the things that make them work. So the current is going through here, creating a north pole here, south pole here. Of course, it's repelled by this north pole, attracted by this south pole. This is repelled by the south pole, attracted to the north pole. So it turns it. This happens to be in a counterclockwise direction, the way it's set up here. And as long as this is touching this split ring commutator down here, the brushes are touching, the current's flowing that direction, and it gets it moving here. And it wants to move until it would line up like this, and the north pole here would be with south, and south with north, and it would want to stop right there. But right a little before it gets there, and it's still moving, it has momentum, then the split ring commutator, the brush touches the other one. Well, now this one that was, say, positive is now, this stays, let's call this negative and this one positive. As long as it was touching the positive, it had a current flowing in that direction. But as soon as it leaves that one and touches this one, now the current flips. When the current flips, then that north changes to a south, this south changes to a north, and now it's repelled from the this one that was a north is now a south. Now it's repelled by the south. This south that was the south now becomes the north when the brushes hit the other half of the commutator, and now it changes, and now it keeps it turning in the same direction. And that's exactly what happens. As long as those brushes are touching one half, they're in one direction. As soon as they flip over and touch the other part of the split ring commutator, they change directions and then change the magnetic field of the electromagnet. And see, electromagnets can change that quickly because they're not permanent magnets. These are permanent magnets. They do not change. The electromagnets change every time the current changes. Okay? Now, I think we've hit it. Armature is the movable part. The armature rotates by interactions with the field magnet. The commutator and brushes reverse current as soon as they start to line up where they want to stop. They flip the current because of the brushes hitting on those split rings, and then it reverses the current, and now it keeps it moving in the same direction, repelling and attracting, and then attracting and repelling, and then repelling and attracting. Just keep it turning. That's how electric motors work, based on that split ring commutator in the middle. Okay? Now, everything we set up to this point was that moving charges create magnetic fields. That's what makes electromagnetics work. That's what makes solenoids work. That's what makes all these devices do. Your motors, your speakers, your receivers, all these things operate on that principle. Moving charge induces a magnetic field. Now we've got the reverse of that. We've got a changing magnetic field induces electricity. And this is called electromagnetic induction. The causes is the relative motion between a magnetic field and electrical conductors. The changing magnetic fields near conductors induce electric currents. So on the last thing we were talking about, a moving charge creates a magnetic field. Now we're talking about a changing magnetic field induces an electric current. So one does one, the other does the other. This is basically what James Clerk Maxwell did in his Maxwell's equations. He tied these two things together, and because of that, we can do this. So here's what the situation is. We have here a coil of wire, okay? These are conducting wires, so electrically conducting wires. But there is absolutely no battery associated with it. None whatsoever. No power source, okay? But it's connected to an ammeter. Now that could be a voltmeter as well. It doesn't really matter. I'm just assuming it's an ammeter, okay? And what you do in that coil of wire, you take a magnet, a bar magnet, and you lower that bar magnet through the coil of wire. When that north pole goes through that, you're changing magnetic field. It has to be moving. You can't just drop it in there and hold it in place. No current is created then. Okay? But it's the changing magnetic field through the coil that induces current. So then that north pole moves through, it produces a positive current, let's just say, for people. Now, if you continued it on down until the south pole moved through, then that would then create a negative current because it's a changing field lines. But, on the other hand, if you had the south pole moving up through it, that would induce a current in one direction. When the north pole went through, it would induce the current in the opposite direction. So this is how you get a changing magnetic field induces an electric current. A moving charge, that's a current, induces a magnetic field. A changing magnetic field induces an electric current. Yin and yang. One produces the other produces the one. And basically, that's what's happening in electromagnetic radiation, EM radiation. You have those changes constantly, and one produces the other, and that changes, produces the other, and that's what sends the field through space. Okay? Doesn't need any material there, it just needs the field. All right. Now, before we were talking about electric motor, in which a electrical energy is converted to mechanical energy. Now we're going to talk about generators, and what a generator does is take kinetic energy, mechanical energy, and converts that into electrical energy. So it does exactly the reverse of a motor. And here's Dominique. Okay. Gaining some, losing something just about all the time here. Okay. So here's the structure. Here you have an axle, just like you had an axle in a motor. Main wire loops in a magnetic field. Of course, the same thing as we had before. Okay, here's your magnetic field. The north on this side, the south on this side, permanent magnetic field. This one shows the field lines here. Okay? Now let's say that you have something that is turning your whole system here. That's your mechanical energy coming in. Something that's turning. You're turning this loop. Now they show a single loop. In reality, it would be multiple loops. Okay, inside this permanent magnetic field. Okay, but what you're doing by turning that right now, the maximum number of magnetic field lines are being cut by that loop. Okay, now if that was fixed, no current is produced, none whatsoever, no matter how strong those magnetic field lines are. Okay. Now, actually what this is showing, this is a field core, so this isn't a permanent magnet. This is an electromagnet that you're creating, and you can make it stronger or weaker or whatever by the number of coils that you have or by the current that's going through those coils. But anyway, it just acts like a strong magnetic field. Okay? Now, if something's up here turning this, okay, then as it turns, the number of field lines being cut is lessened, decreased. The maximum number of field lines coming through now, the number of field lines gets less and less as it turns. So that's a changing magnetic field. A changing magnetic field induces an electric current. So you have a current that's now flowing through here. And we'll have, these are your terminal brushes here and here. I don't know why they show them here. But, no, these are where it's connected here. Terminal brushes. So this is creating a potential here, and it's leaving. Now, as that, whatever the outside source, it could be water at a hydroelectric dam, it could be your steam turbine at a coal fire or a natural gas fired power plant, it could be anything that's making it turn. When it turns, then it's decreasing the field lines cut, then it increases, but in the opposite direction, and then it decreases again, increases, decreases, increases, changing direction. This creates AC. You are creating electrical energy from the mechanical energy that's turning the coil. Okay? And that's exactly what an AC generator does. As it's increasing the field lines being cut, you're increasing the current in one direction. Then when the number of field lines being cut goes to zero, that's zero, but then as you're increasing in the other direction, you have this is positive, negative, that's your AC generator. Alternating current, the sign of the current and the voltage always alternate. Okay. They don't quite do it in phase. There's a 90-degree out of phase there, but they still alternate. That's AC alternating current, AC generator. Now, in order to make this a direct current, and sometimes we need that. For instance, where's one place you need your generator to produce direct current rather than alternating current? Your car engine. What is it? What's your your source for electrical energy in your car? What's that?
The source for
Electrical energy in your car.
not the battery.
The battery, exactly. The battery is there, and when you go to turn on your car, you're connecting the battery to a electric motor, which we saw several slides ago, and that takes electrical energy, converts it to mechanical energy, turns the motor, gets it started, and now your internal combustion process picks up, and now that is producing your motion. You're not turning with the battery anymore. You turn off the switch, but your car keeps running, or you release the switch from the starter position. Well, your battery, you just ran it down some. So what you do now, once the engine's running, it also, in addition to providing motion for the car, it also is turning a little electric generator. And that electric generator is going to be used to recharge the battery. But a generator usually produces AC current. Well, AC would be charging half the time and discharging the other half time. So it'd be charge, discharge, charge, and you wouldn't build up any in your battery. So you need a DC generator to rebuild your battery, to recharge your battery. So you need direct current there. And by the way, that's what, anytime you have a device that has a box between the plug in the wall and the device, that is going to be changing AC coming in to DC going out. This is called I'll read it off of here, an AC adapter, okay? It adapts from AC to DC. And I've seen some of you plug it into the wall. I don't see anyone plugged in now, but what do you have there? A little box, and then you plug the thing into it. That little box is just like this big box. It's converting AC to DC. Well, what is your DC generator doing? It's producing direct current, but the sign of the current and voltage, the sign is constant. The amount is not constant. Here's how it works, okay? In this case, we have another split ring commutator here. So now when you get maximum field lines being cut and they're decreasing as the mechanical energy is moving this around like this, so it goes to zero. As soon as it turns that halfway and starts to turn again, the brushes now touch on the other split ring. So now what was sending out positive this way and negative that way, as soon as they flip, and then it would be sending out negative and positive, now they flip and send in the opposite direction. So the negatives always go one way and the positives always go the other way. So this produces what we call pulsed DC. Because as soon as it hits that split ring, it flips its direction so it goes back up again, and then up again, and then up again. So you have a pulsed DC current. The sign and the current and the voltage is always constant. They show in positive here. It could be negative. It doesn't matter. And but the amount of it is varying, is pulsing, but it's still all in the same direction. So these little pulses recharge your battery because they're all going in the same direction. Does that make sense? Not that anyone's listening. Okay. So, now, there are times, and by the way, let's go back. There is a pretty interesting little concept supplied here. I don't know if you want to try it. You could do it at home if you wanted to. Okay? You could make a lemon battery. It doesn't have to be a lemon. It could be an orange. It could be grapefruit. It could be anything like that. All you need are two dissimilar metals. They show here a paper clip, which is mostly iron, and a wire, which is copper. Okay? Two different metals. Stick them into different places in the lemon, or lime, or orange, or tangerine, or halo, or whatever citrus that you wanted to do it in. Probably would work in, what's the green fruit? It's real citrusy. I can't even think of the name of it. We have some in the fridge right now. I can't think of the name. But doesn't matter. Stick in any of those that's really strongly, especially if it's pretty strong acid fruit. Doesn't have to be acid. Stick them in there, and then you can wrap a coil, tie a wire around that, wrap it around a compass, and you'll see that the compass needle always points in one direction. Second? Orange or anything else like that, yeah. It'll work. You need two different metals, paper clip, copper wire. Anything such as that, stick it in, wrap it around a compass, and the compass may be pointing anywhere it wants to. As soon as you connect that, it'll line up right with the magnetic field of that coil. Okay? So that was an interesting, they call it a lemon battery. And by the way, now I ask this when I'm teaching my automotive students, and they all say yes because they really are taking me literally. I say, have you ever had a battery in your mouth? And most of us don't ever put batteries in our mouths, do we? Well, all the automotive students do, just to see what it's like, okay? And if they put their tongue against a 9-volt battery, they're going to get a little tingle, maybe a big tingle, you know. But what I was talking about is this. Now, if any of you have perfect teeth, you've never had a filling, this will not work for you, okay? But if any of you have ever had a filling, especially the old silver composite filling, I've got several of them. If you've ever bit down, say, on a piece of aluminum foil by mistake, did you know it? Try it. Take a little piece of aluminum foil, if you have a filling in any tooth, okay, stick it in your mouth and bite down on it. You will know you bit down on it because it sends a little jolt of energy into that filling, and that filling is close to your nerve. You're going to feel it, okay? You just put a battery in your mouth. What a battery is two dissimilar metals, aluminum and silver. Dissimilar metals. You bit down with an electrolyte in between. Your saliva is a great electrolyte, and you just made a little battery. And what you've measured by your nerve endings beneath your tooth, you measured the voltage and the current that came through there, and that was significant. So that's what they mean. They called it lemon battery. I call that a battery in your mouth. Okay, now by the way, the 6.5 was electromagnetic induction. We've already finished that. And they talk here about a simple generator, and you can look at that if you want to. There is also on page 163 a little blurb at the top of the page that is probably, for a little blurb, has some of the best and most compact information you could get. It's talking about three individuals here. Thomas Edison, who was probably the greatest inventor that America has ever produced. I think at one time, I imagine he still does, held more patents than anyone else in history, okay? He was just so creative electrically, okay? The electric light bulb, of course, and things about the phonograph, and just all sorts of things. He had patents for it. But he was absolutely sold on the fact that DC was the only way to go with electricity, because he thought AC was way too unstable and dangerous. You didn't want to use it. Well, there was another individual mentioned here. His name was George Westinghouse. If any of you have any refrigerators, washing machines, or other things that are Westinghouse, named after him, okay? Now, my uncle was a electrical engineer, or civil engineer. He didn't care for Westinghouse products too much, so he called it "We Sting Who Use," but that's not the same. Westinghouse was in the business of supplying gas for gas lighting. He could see electrical lighting would soon be replacing that, so he started to go after that. He found out Edison's low voltage system was not enough, so he started experimenting with generators and transformers. in Pittsburgh, not in New York. Well, Nikola Tesla, okay, he's a Croatian-born, that's over there in what used to be Yugoslavia, but Croatian-born U.S. physicist and electrical engineer who moved to the U.S. and worked for Edison for many years, was incredibly creative with Edison, but they had diametrically opposed views. Edison was sold, convinced DC was the way to work, and the more he studied it, Tesla said, nope, AC is the way you got to go. And they fought and argued until they broke up and went their separate ways. Well, Tesla teamed up with Westinghouse, and guess who won? AC is who won. That's one place that Edison wasn't right on the money, okay? Westinghouse and Tesla. So there's three different people, the whole AC-DC battle, the war of the currents, whatever you want to. There's several potential paper topics right there in this little blurb. And by the way, your research papers are due next Tuesday or before. I will take them anytime, but the last date that I'll accept them without losing points is next Tuesday. After next Tuesday, you start losing points, okay? But up till Tuesday, you don't lose points, but please get them in sooner than Tuesday if possible, okay? So, several potential topics right there. Okay. Now we're ready for transformers. This is beginning on page 163 in your book. This is under 6.5, electromagnetic induction. And this is the slide on it, transformers. Here's the problem. If you're sending current long distances through wires, the wires themselves, even they're the great conductors, they do have some amount of resistance. Now remember, one of the features that contributes to the resistance was the length of the wire. And if you're sending through wires that are miles and miles and miles long, you're losing current. You're losing energy, big time, producing heat. So there's a problem in power transmission. This is even worse probably in Edison's DC, but it's still bad in AC. Now, what is it that loses the power? The high currents. There you have large resistive losses. The more current you have, you have larger and larger. Now, if you had high voltages, okay, then you have dangerous potential differences. So people can get badly shocked with different changes in voltages, potential differences. So here's what the solution is. In our homes, in our buildings, in places like this, the voltage is right around 120, 110, 120 volts. Now, if you've got big devices such as washing machines, not washing machines, dryers, ovens, heat pumps, and things like this, you're actually using 240 volts, not 120, okay? But it's relatively low voltage. Now, for things like your yard lights, if you have lights that show up under trees and windows and things like this, lighting paths, you drop the voltage even lower, maybe 6 to 8 volts or something like that. So you want pretty small voltage differences. But there you tend to have larger currents, okay? Well, larger current, you have high resistive losses over long distances. So what we do, we put up transformers. And if you'll notice, wherever you live, in a house, an apartment, whatever, if you look outside to where the wires come into that building, on that power pole where those wires come from, you're going to see a device like that. That is what we call a transformer. What it does is take the relatively high energy, high voltage transmission that's coming to the pole and transform it into lower voltage, higher current, and that's what goes to your house. And that's what we use. Typically, low voltage, relatively high current. If we tried to send that for several miles, now the few yards between the pole and your house, that's not going to lose a lot. okay? Just not going a long enough distance. But if you were going miles and miles at that, yeah, you would. So even to get to the next transformer, you jack up, the voltage is higher in the wires that are going here than the wires that are going to the house, okay? So the transformer boosts or lowers the AC currents and voltages. Because if you lower the current, you're increasing the voltage. If you increase the current, you're lowering the voltage, okay? Now, at the generating plants, whether it's the hydroelectric plant up there at Smith Lake or whether it's the coal-fired generators that are producing it out at, I can't think of the name, but if you go Highway 22, on the way to Jasper, you go by a couple of plants, you always see either smoke or steam coming out of those pipes. There's some sort of power plant going on there. Whatever it is, when it's leaving there and heading out from there, it's going through high voltages. You take transformers and boost up the voltage, dropping the current, so you have very little line loss. Now, the farm that we have in Burke County, Georgia, is in the same county the new plant. Well, Plant Vogel's been there a long time, okay, 30 years probably or longer, 40 maybe. Okay, that was a nuclear power plant. And recently they added an additional nuclear reactor. The first one added in the U.S. since 3 Mile Island happened probably 30, 40 years ago. So, and they needed, because Atlanta and other places needed more electrical energy. So those big power lines, they needed a way to cut through and get them to where they needed to go. And part of the pathway went really close to our farm. And they had asked if we would mind those power lines coming across the farm, and my brother, who works for the local power company, said absolutely not, because we would get some revenue from that. But they wound up doing just basically within sight of the farm, but they didn't actually cross our farm. But I passed under them 2 or 3 times going to and from the farm, and those are really high voltage, very low amp, because those are going hundreds of miles to where they're going to use that energy. Okay? So that's what the transformers do. They step up the voltage when they leave the generating plant, travels over long distance. They step down the voltage, usually 2 or 3 times when they come into a city. And you'll see places like, I know at UAB, they'll have sometimes an entire city block there, all cordoned off. You can't see chain link fence, but you can't see through it. And that's just a big transform station where they're taking high energy, high voltage, coming in and dropping the voltage to where they're going to send it around campus, and they'll drop voltage again right before it goes into the building. So that's what transformers do. They boost or lower the currents and or voltages in opposite directions. Here's the basic relationship. The power in is equal to the power out. Now, I don't know if y'all remember electrical power. I think we did this earlier. Let me make sure. Pretty sure we did. Electrical power, I'm pretty sure Bree was the one answering this because that was one of her bags. Let me get my, okay. Electrical power is voltage times current. That's what power is. I'm pretty sure we went over this. What is voltage? Voltage is joules per coulomb, energy per unit charge. What is current? That's charges per second, charge per unit time. The charges, coulombs, cancel out, and that gives you joules per second, which is what a watt is. So yeah, power is equal to voltage times current. So power in equals power out. So that means voltage in times current in is equal to voltage out times current out. Power in equals power out. But you can change the voltage and the current. They change in opposite directions, and that's what does it, is the number of coils that are in your thing. You see, and we'll show a picture of it in just a minute. You have coils on one end and coils on the other end. And the ratio of the number of coils, that's what this is referring to. The incoming voltage on the primary side, what I call the N up here, I up here, this is the primary side here. The ratio of that to the number of coils on the primary side is the same as the ratio of voltage on the secondary side to the number of coils on the secondary side. That's the number of turns per unit, well, per coil, okay? So you have different numbers on incoming and outgoing, and according to that, you have different voltages. So the higher the number of turns, the higher the voltage, the lower the turns, the lower the voltage. Okay? All depends on the number of coils and how that relates to the voltage. So that's what our basic premise is. Let's see how it operates. Oops. There was a reason that was a blank spot there. And here's what it is. Okay? So let's say that you have 120 volts on this side. And you have 10 turns of the wire around your electromagnetic core here. Now, remember, this is AC, 120 volts, AC, constantly changing voltage, positive, negative, positive, negative, positive, negative. What does it take to induce a magnetic charge? A changing electric field. This produces a changing electric field. So that induces a changing magnetic field. The changing magnetic field induces an electric current. And that's what you have over here. But where you have 10 coils turns here, 20 to 10, that's a ratio of 12 to 1. Well, here you only have one turn here, so you only get 12 volts out. The current is much greater here than it is here, but the voltage, this is called a step-down transformer. Steps down from 120 volts to 12 volts. This would be that box, if you have any exterior lighting. And we have some around our house. My wife really wanted some. We set up some ourselves where they blew out, and she said, I'm tired of fixing these. So she hired a guy. He's supposed to maintain it. So far he hasn't. So she's going to call him because the lights are beginning to flicker. But anyway, he stepped down from 120 volts, I think, to around 8 or 10 volts. This shows it down to 12 volts. Increases the current, but it decreases the voltage. Okay? However, if you had 120 volts coming in here, only had one turn here, that's a ratio of 120 to 1. What if you had 10 turns over here? Whoa, you've stepped up the voltage from 120 to 10 times as much, which would be 1200. So now you got a big voltage going out. You don't want to do this at home. That gives you such a huge voltage difference. But this is what they would do at the power plant. Before they send the electrical energy down a long wire, they would want to step up the voltage. Why step up the voltage? It cuts down the current. When you cut down the current, you reduce your resistive losses. It's that principle. Okay? So there's the formula we use. Voltage on the primary side, the ratio of voltage to coils on the primary side has to equal the ratio of voltage to coils on the secondary side. Okay? So let's do example 6.9. A step-up transformer has 5 loops on the primary side. Let's see. Let me just draw it here. Here is your core, and you have 5 loops on the primary coil. 1, 2, 3, 4, 5. Okay? So that's 5 loops on the primary side. This is the primary side. And 20 loops on the secondary side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 loops on the secondary side. Okay? If the primary coil is supplied with alternating current, if it's DC, you don't get anything. Alternating current, though, you do get something. Alternating current at 120 volts. This is primary side, so N sub P is equal to 5. V sub P, they just told you on primary side, 120 volts. Okay? Now, what is the voltage on the secondary? So your N sub S is 20 loops. So your V sub S, that's what we're looking for. What is the voltage on the secondary side? Well, there's several ways you can approach it. I think the most direct would be, what is the ratio between VP and NP? 120 divided by 5, that would be 2, pretty sure that would be 24. So that's a ratio of 24 to 1. That's going to be the same on the other side. 24 to 1 is voltage to loops. Okay? And this is a proportion, really neat to deal with. You got a 24 to 1. This is volts to loops. Okay? As over here you have V volts, same unit, as to 20 loops. Okay? Well, you multiply these two together and you get 4, 8, 0. And multiply those two together and you just get 1 times V. So V is equal to 480 volts. So you've stepped up transformer from 120 volts to 480 volts because you have, and here's the other way to look at it. This is a 4 times here, 5 to 20, that's 4 times. So your voltage is going to be 20 times 4, which is 480. 120 times 4, which is 480. Either way you do it, you get the same thing. Step up transformer. Okay? Now, 480 volts. Then there's example 610. The step-up transformer in 6.9 is supplied with alternating current at 120 volts and a current of 10 amps. So your IP is equal to 10 amps. Okay? Now, that's a different formula here. I gave that to you at the very beginning. Does anyone remember the relationship between current and voltage? Some of you weren't in here at the time, and what you're looking for is IS, the current on the secondary side. Anyone remember what that relationship was? Those who were here and were paying attention and cared. Anyone remember? It was really what we had at the very beginning, power in equal power out. And what's your electrical power? Power in equal power out. Electrical power is voltage in times current. Current in is equal to voltage out times current out. There's your power formula. Okay? We already know that you had 120 volts in, and this told you you had 10 amps in. Okay? I think it was 10.0 amps. No, it isn't. Yep, it was 10.0 amps. Okay? And that's equal to voltage out, which we just determined was 240. This is our secondary. So this is 480 volts times current out. Okay, so this time we divide both sides by 480 volts. Okay, and here the volts cancel out. Here everything cancels out. And 120 will go into 480 4 times. We knew that. 2 will go into 4 twice. 2 will go into 10 5 times. So you get 5 divided by 2, which is your current out, is equal to 2.5 amps. 10 volts coming in, 10 amps coming in, 2.5 going out. Why? Because your voltage in was less than your voltage out, much less, by a factor of 4. So you divide 4 into this to get your output current. You multiply the current, the voltage, you divide the current, about the same ratio. So 10 divided by 4 is 2.5. 2.5 amps out. Make sense? Okay, and Brandis is here. Somewhere here I have my watch, so I can keep up with the time here. Okay. We're getting close to 3, and we go to 3:45 today. No test today. It's 3:45. Okay. Everybody understand then example 610. Now, before we get to 6.6, which is current circuit connections, which is the next slide, there is an interesting little blurb here. I don't know if you've ever seen one of these, but they really are interesting to see. If you have a coil of wire suspended here, okay, and it's connected to another coil of wire suspended somewhere else. It could be very long distance away, it could be in the same room, it could be in another room, okay? And this coil of wire is over a pretty strong permanent magnet. Fairly close, not touching, pretty close. This coil of wire is also over a very strong permanent magnet, but it could be a room away or anywhere, okay? If you take this, now this is suspended there, and you just flick it or something and make it start swinging. Now notice there's no current, there's no voltage anywhere in the system. There's no battery, nothing else. They're just wires, just wires. You start that one swinging, go over to the next room and that one starts swinging. Why is that? Because this is a magnetic field here. When you start this one swinging, you're cutting different number of field lines by the swinging coil, and that changing magnetic field lines being cut by a coil of wires induces a current in here. When you induce a current in here, in the presence of that magnetic field, that starts its swinging because they interact. The electric field and the magnetic fields in both cases are interacting with each other, and they split. And so therefore you'll get this kind of motion going on. Whether they're close or far away, it doesn't matter. Okay. And here's Samaya. All right. We've wound up with a pretty decent sized class today. Still missing a few. A few were here earlier and had to leave. Family and other issues. Okay. Oh, and by the way, they got 2.5 amps too, just like we did. Okay, so now we move on to 6.6, which is circuit connections. Now, we've talked around and about this in several ways, but let's just sort of summarize it here. Most of what we use coming into our houses, leaving our houses, well, nothing much leaves our house, is alternating current. That's what comes into the power lines. That's what's in every plug that you have down here is alternating current. Okay? Practically all generated electricity, if you have turbines, whether it's water turbines, steam turbines, gas turbines, whatever kind of turbines, those are producing alternating current, okay? And we'll see that when we do the lab today, okay? Now, these are transmitted over high voltage lines, step down before they come into the homes or the buildings, okay? That's what we're talking about with our transformers. That's where we live. We produce alternating current, we use it. However, there's a good number of places we use DC, direct current. Now, it used to be these were largely dealing with batteries. Anything that has a battery in it is going to be DC, okay? And what is one device you drove to school here in that had a battery in it? A car. Just about everything in your car is direct current. You have a little generator in your car that produces alternating current, except it has a split ring commutator, which changes it to direct current. So just about everything in a car is that. Your cell phones, she's plugged into the wall right here. She plugged into an alternating current, but what does she have between where she plugged in and when it goes to her phone? That little white box. That is some people call it a transformer. It's not quite, it's not good to use those terms. It's what did this call it? Adapter, okay? AC adapter. It adapts the alternating current to direct current so she can do that. That's exactly the box I picked up. Alternating current coming from the wall, direct current going into my laptop. All these devices, MP3 players, anything that has a battery, DC, okay? And if you have a rechargeable battery, you're having to have some sort of box there that adapts the AC to DC, okay? Now, most of your movable, portable applications that you would have a battery in, you can't plug into a wall somewhere, you can't have a cord when you're running around the block listening to your MP3 player. You have to have batteries. Those are going to be direct current. The main current source is chemical batteries, even chemical batteries that you can recharge with AC, as long as you have the adapter, okay? Now, have any of you traveled much overseas? Yeah. My wife has to travel with, she's a research professor at UAB, so she has international meetings, maybe once every other year, sometimes more than one a year. So she does have to travel out of the country. I've been out of the country a few times, either with her or otherwise. When you do that, you have to be very careful. Find out where you're going to, what they use. If you take your cell phone, plug it into theirs, you could blow your phone. My niece did that, I think, or her friend did when they were traveling in Europe. Forgot to plug in the adapter one time, completely destroyed her cell phone. Brand new, almost cell phone. So you have to be very careful with that. Because different countries, like Europe uses mostly 240 for their in-the-wall thing, whereas we use 120. Okay? So you have to be very careful. Okay? That's not what this section is talking about, but just since it was up there, I brought it up. The voltage sources in circuits. Now, we did this in the very first lab. I hated that we did it, but all we were talking about was circuits there, but the lab tied in the circuits with the series and parallel. So let's look at this one. This is one type of a series circuit, but this type of series circuit is your batteries are in series, not your volts. The batteries in series. This is when we turned up the juice or turned down the juice. Remember, when we went from one pair to two pairs. We doubled the voltage or not. That was like we were adding another dry cell. Okay? Now this is a series circuit. The same current flows through every part of the circuit. Okay? You add another battery, you get more current. Okay? Because you just increased the voltage for the same resistance. The negative terminal of one cell is connected to the positive terminal of the next cell, to the negative terminal here, positive there, and back around. All the way. Okay? The total voltage is the sum of the single cell voltages. If this is 1.5 volts, that was 1.5 volts, that was 1.5 volts, you have a total of 4.5 volts there, your light's going to be very bright. Okay? May blow it out. Okay? Single current pathway, that's what we mean series circuit. Single current series. Okay? Now that's with your batteries in series. You're just adding the voltages. Okay? This kind of setup, the batteries are in parallel. Okay? Your positive here to the positive there to the positive there, your negative here to the negative here to the negative there. Well, guess what? All the negative terminals connect, all the positive terminals connect. The resultant voltage is the greatest of these three, whatever the biggest. If this was 1.5, this is 1.2, and this is 1.7, this would be a 1.7. Okay? But they don't add because it's whatever the largest voltage. The resultant voltage is determined by the largest cell voltage. If all of them are 1.5s, then you have 1.5. The bulb is not going to be very bright. What would be the advantage of doing this, though? What would you get out of that? Longer battery life. Because you see, each battery is only having to provide a little bit of current. And the use of the current, that's what uses up the battery. So, because you have, basically you have a bigger battery here. You have 3 batteries all at 1.5 volts, and so it can last a lot longer. So if you had this up on the top of Mount Cheehaw, some remote weather station up there that didn't have a place you could plug it in, and you had to climb up there and change the batteries anytime they went down, you're going to want to put as many of those in parallel as you can so you don't have to change the batteries as frequently. So that's what you get, longer battery life. Okay? Makes for greater electrical energy available, meaning for a longer period of time. Okay? Same electrical energy available, but for a longer period of time. The bulb's just going to be standard brightness there. Okay? Because those are in parallel. We couldn't do that in the lab because we either increased the voltage or didn't increase the voltage. So we didn't have batteries in parallel. But in this case, it's your resistances that are in series because it's the same current flowing through every device. Now I put my finger this way for the conventional current. They're showing electron current going the other way. It doesn't really matter. And in here, because it's series connection, the total resistance is the sum of all the components. If this was a 10 ohm resistor, and that was a 10 ohm resistor, and that was a 10 ohm resistor, you have 30 ohms in that current. You add up the total resistance. These were different resistors, you add those up, 10, 12, and 15. That would be 37 ohm resistance, okay? Now, the more of these you put, the larger the resistance, same battery, the less current you get. So these bulbs will get dimmer and dimmer and dimmer. And you saw that in the lab. If you remember that, this was 2 labs ago, when you put 2 bulbs in series with only 1 battery, they were dimmer than either one of them before. They were less than the standard brightness. Okay? The current drops, the more elements are added. Okay? Because you have the same voltage, more resistance, the current has to drop. Ohm's law. Okay? Now, here's the weird one. Oh, they just lost that. Oh, here's the formula. The resistors in series, you just add the resistance. So the total resistance would be R1 plus R2 plus R3 plus however many resistors you add, the more you add, the more they drop. Okay? The greater the resistance. Now, okay. Don't give an example, but it wasn't the right one. Okay. However, what if you have your resistances in parallel? Okay. By the way, this is on page so looks like there's an example here. Should we do this example first? No, we haven't quite gotten there yet. We could do it because, okay, let's do this one. All right, we're going to do this one first. Okay? This is example 611 on page 167. Okay. 3 resistors with a resistance of 12 ohms, 8 ohms, and 24 ohms. These are your resistors, your light bulbs here, okay, are in a series circuit with a 12-volt battery. Most dry cells are not 12 volt, but imagine this was a car battery, okay? All right. What is the total resistance of the resistors? You add them up. In a series circuit, you add them up. So this will be 12 ohms plus 8 ohms plus 24 ohms, 24 ohms. This would be 20 and 24, 44 ohm resistor. That is your total resistance of that circuit. Okay? And that's exactly what they've got here, the A part. What's the total resistance of the resistors? The B part, how much current can move through the circuit? Well, you have 44 ohms of resistance and 12 volts of voltage, potential difference. What law do we use there? Whose law do we use there? Ohm's law. And how does that go? Say again? A little louder. Still can't quite hear. I thought I heard a P. Did I? Say again? No, say it. Not P. Ohm's law is what? Y'all did it in the last slide. Over and over again. Okay. You weren't here. Okay. Okay. She has an excuse. What's the rest of your excuse? Okay. Ohm's law. How does it go? Anybody? Oh my. Okay. There's one of 3 ways you can do it. Voltage is equal to current times resistance. Or divide both sides by I, and you have resistance is equal voltage over current. Or divide both sides of the original by R, and you get current is equal to voltage over resistance. Or you could do your triangle or your circle and set them up. That's all 3 of those express Ohm's law. What are we looking for here? It says the B part, what is the current? So in the B part, we're looking for current. So that's voltage, I, is equal to volts over resistance, and that would be 12 volts divided by 44 ohms. Anyone got a calculator? Do 12 divided by 44. If you want to be a little cheaper, you could say 6 divided by 22, or even 3 divided by 11. What you get? 0.37 you said? Huh? 27? Okay. 0.27 amps. That is a 2. My hearing's bad, so I couldn't understand what she was saying. Okay. 0.27 amps. That's the B part. This is the A. Whoops. Here's the A part. Here's the B part. Okay. The C part said, what is the current through each resistor? What's the current through each resistor? Guess what, team? In a series circuit, the same current flows through everything. So if the total current in the system is 25.27 amps or 270 milliamps, that would be in this one and this one, that would be the same. So it would be 0.27 amps in each. Okay? Now, you can also do this, and this is very legal. Okay? If you got 0.27 amps here, from this one, the voltage drop, and this would be a delta V. A drop in voltage would be this current, 0.27 times 12. Someone multiply that for me. 0.27 times 12. 0.27 times 12. Not that hard. about 3 or 2 point something. What you get? 15.14. No, it's times. It's not divided. Okay. 0.27 times 12. It's only going to be around 3 or so. What you get? Second? Whoa. 0.27 times 12. That's a quarter of 12 is around 3. Second? 3.74?
3.24.
3.24. Yeah, that makes sense. Okay? How about 8 times 0.27? 2 point something. 2 point what? 16 volts. How about 24 times 0.27? That should be 6.48 or something about like that, right? Yeah, something like that. Add those three together. 6.48 plus 2.16 plus 3.24. Second? 11.88, awfully close to 12. We had a little bit of round-off error, that's why we didn't hit 12, but it's awfully close. That would be 11.9, and that would be almost 12. Just because we had the round-off error. First, you round it off here, and then you round it off here, and you round it off here, and you round it off there. So all that round-off error adds up, okay? But yeah, that's your setup, okay? That was your series. So let's now go to, and it was based on the fact the resistance add, the current stays the same, the voltage is split. Okay, you probably remember all that from lab. Okay, parallel connection, more than one current path is available. You see the current leaving from this dry cell here, the battery here, some of it goes to this one, some of it goes to that one, and some of it goes to that one. You have 3 different paths the current can take. And that's why when you remove one bulb, the other 2 stayed on, because they still had paths to get there, right? So this is your parallel connection. More than one current path is available. So you have different current going through here, then there, and then back down here. Because they currents add together. The overall resistance, now here's the strange thing. The more light bulbs you put in this, the overall resistance actually drops. Why is that? Because your poor old battery here is having to provide current for this one, plus current for that one, plus current for that one, plus everyone you adding more and more current, so the overall resistance has to go down because your current is going up for the same voltage. Strange but true. The total circuit current increases as more elements are added, because your poor old dry cell stays at this fixed voltage here, and the more bulbs you put, that same voltage is across those, so then it happens to provide more and more current. Now this is what I was going to give the example. I realized I was giving it backwards. I needed this one. We have a little greenhouse in our backyard. It's not very big. We put it together. We bought the kit, put it together. It was a pain in the neck, but we got it done. And we did that so some of our ferns and other plants that we have on our patio in the summertime, we didn't have room to store them all in the garage. We didn't want them all in the house, so we wanted them in the greenhouse. And that way it would keep it a little warmer in most days. But at night, it would get pretty cold in there, in the coldest part of winter. This winter, we only had to provide the heat just probably no more than 10 or 12 nights, okay? Maybe not that many. So what we're going to use to provide heat? Well, we had these little heaters we can take from the house and put out there, but we really didn't want to because we were using them in the house. And then my wife read about the old Christmas bulbs. Not the old ones, but the old ones that got so hot and they dried out your tree, and they encouraged you not to keep them on too long. Well, people got away from them because they went to safer ones that didn't dry out the tree as much. So a lot of people still have these old bulbs. So I asked my brothers and sister if they had any. Oh yeah, we've been wanting to get rid of those. We just forgot to have thrown them away yet. Well, could we have them? All right, so I bought them for my sister. And so we got a bunch of those and put them in the greenhouse. It makes the greenhouse look really pretty when it's a cold night. All those colored lights are on, but it also provides heat because those old bulbs got hot. Well, I found out that I could only string 2 strands together because the more you added, those were in parallel, the more current it was drawing, and they blow the fuses. Because each one of those had a little fuse in it, and when it got too much current, they blow it. So I could only do 2 strings together, so I got a 3-prong plug and did one for each because there wasn't a fuse back here. They were in line fuses. So anyway, the more things you put in parallel, the more current you're going to draw. Okay. Total current increases the more elements are added. Okay, now here it is. Here's how the resistance is added in a parallel connection. Really bizarre, but true. 1 over the resistance total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and you keep going. The more resistors you add, you're adding these, but then when you get to this, you invert it and you decrease the total resistance. Incredible, but true. Okay? Now, there is a key on most of your calculators. Maybe your phones, too, is the 1 over X key or the X to the minus 1 key. I'll write that down for you. In fact, I'll write it down here. It's either a 1 over X key or X to the minus 1. If you can find that key on your calculator or phone, that's going to be the easy one to use here. And this is going to be example 612. Okay? Assume the 3 resistors in example 611, and this was, now let me go back to the picture here. 12 ohms, 8 ohms, and 24 ohms. Okay, are in parallel now, not in series with each other. Okay? Whoops, went the wrong way. All right, so I'm going to take these off here and put them down here. 12 ohms, 8 ohms, and 24 ohms. Okay? Assume the 3 resistors in example 611 are now connected in parallel. What's the combined resistance? So that's what this gives us. I like to call it effective resistance because total makes it sound like it's bigger. In this case, it's smaller. Okay? So here's what you do. If you have that key, one of those 2 keys, 1 over X or X to the minus 1, you type in 12 and then hit that key, reciprocal. It makes it a small decimal number. Plus 8, hit that key again. Plus 24, hit that key again. Equal, that gives you a number, and then hit that key one more time, and that gives you total resistance. Every time you hit the key, you flip it either top to bottom or bottom to top. Did y'all do that as I was saying it? Okay, you want to try it? Did you do it? 4 on the nose? You got it. The R total was 4 ohms. Now notice here, the total resistance was less than any of these resistances. Less than any of them. So the more you add, the more it drops. It sounds crazy, but it's true. Your effective resistance is 4 ohms. Okay? So there's your answer to the A part. Okay? 4 ohms. What is the current in the overall circuit? Okay? Well, this is the B part. The current in the overall circuit, and you know your voltage. Let's go back to this picture. This voltage, remember, was 12 volts. Okay? So if the voltage is 12 volts, What law do we use here? Whose law? Oh, how soon we forget. Ohm's law. And how does that go again? I equal V divided by R. Perfect. And your V here, I is equal to V divided by R. And this is the effective resistance. The voltage was 12 volts divided by 4 ohms. That's what Seth said, right? What would this be? 3 amps. Whereas before it was just over a quarter of an amp. Now it's up to 3 amps. And the more resistors you add, the higher the current goes. Okay? Now it says, the C part, what is the current through each resistance? Ooh. Well, the current through this one, okay, what were those? Yeah, okay. Remember, it's the same voltage across each. We're going to go back here. See this 12 volts here is across, it's between these two, it's between those two, and it's between those two. So you got 12 volts across each of those, okay? I hope that hasn't made too big of a mess here. So you got 12 volts across each. Okay. I think I erased all the mess. Okay. And you want the current across each. So you got 12 volts across, and you got your, let's see, what is the current through each resistor? So current is equal to V over R. The V is always 12, so it would be V over, the first one would be 12, so 12 over 12. 12 volts over 12 ohms. What would be the current in that one? Pretty easy. 12 divided by 12? 1 amp. Okay? And the next one, I2, it would be V over R2. This was R1. That would be 12 volts over 8 ohms. I'm sorry, I'm writing in the space there. 12 divided by 8. Well, 4 will go in each of those. That would be 3 over 2 amps. So that would be 1.5 amps. 3 over 2, right? And then your last one, V over R3, would be 12 volts over 24 ohms. And what's that? 12 divided by 24. 0.5 amps. Well, look at that. Add the 3 currents together, and sure enough, that's what happens, isn't it? You add the 3 currents. This current was 1 amp. This current was 1.5 amps. This current was 0.5 amps. Add them all together. 0.5 plus 1.5 would be 2, plus 1 is 3. That was your 3 amps. Sure enough, it all works out. 3 amps. It's 1 amp, 1.5 amp, and 0.5 amps. Exactly like we got up there. Okay. Now, I think it's the last little section here, yeah, is household circuits. What do we really have going on in our house? Okay? You have combinations of some things in series and some things in parallel. Okay? Let's just think in this room for a moment. Okay? The light switch has to be in series with the lights. Because if that switch is turned on, the lights come on. When it's turned off, they go off. So it has to be in series with the lights. Okay, we got 2 switches, one for this bank and one for that bank. Okay. But what would happen if I took out all the tubes out of one of these? Those would stay on with it. Okay? That means they're in parallel with each other. They're in series with the switch, but in parallel with each other. Okay? Now, she has her phone charging there. Can you tell that it's charging? Can you look at it and tell? Huh?
If I like open it.
Oh yeah, but I mean, yeah. Do you mind doing that? I mean, can you tell that it's on?
Yeah.
Okay, and you see that it's charging. Okay. Now I'm on the same circuit she is. If I unplug mine, did yours go off? No, it didn't. Of course it didn't, because they're in parallel with each other. Okay. Now, yeah, can't think of anything that's being serious with that. So that's what's going on here. Okay. Here we have our circuit breaker box. Most houses have this. Now, the first house we lived in when we moved to Birmingham, we rented, and it was an old house, and it had fuses. Boy, did we ever go through the fuses on that house, because it had so few plugs, and they had added more in the kitchen. And if you ran the toaster at the same time you ran the coffee maker, you blow a fuse. Okay. Or if you were doing things and they were all right, and the refrigerator compressor kicked in, then it blew a fuse. So you just couldn't tell what was going on. So here, the switch is in series with the light, but it's in parallel with all the receptacles. Because when I turn off the switch here, it doesn't turn off the receptacles here. And these are in parallel with each other. So this toaster, which it produces a lot of heat, draws a lot of current. That's in parallel with the can opener, which doesn't draw as much current. So that's in parallel with the radio. It doesn't draw as much current. But the more things you add, the more and more current you're getting because of your parallel circuits. Okay? Now, if it were to overload, they're all in series with your circuit breaker. And if you get too much current through one of these circuit breakers are always rated, 24 ounce, 12 ounce, 15 ounce, something like that. They're always rated. And if more than that goes through, they're going to flip. Okay? And then you take your load off, go back and turn on the breaker again. That's the advantage of a circuit breaker over a fuse. When the fuse blows, there's no returning back. You have to replace the fuse. Now, circuit breakers also will blow. We have one in our garage right now that is blown, and I don't know if I have the skills or ability to know what to do to change that. It's probably pretty simple, but I haven't worked up the courage to do that yet. Okay, it's in the garage, so it's no problem. It's too much. Okay, so that's our household circuits. The circuit breaker has to be in series with everything on there so that you don't overload. Seemed like I was going to say something else about that, but that's probably enough. Now, here's some other safety features about household current. In the old days, and if you're in an old house, you may know this already. The old plugs were just two plugs that were exactly equivalent. The two plugs are exactly the same. It doesn't matter how you plug this in. Why doesn't it matter? Because it's going to go through an adapter anyway. So it doesn't matter which one's going which direction, you're changing it to DC anyway. But on things that do matter, in more modern houses, which could be in the last 25, 30 years, our house is 1930, so it's really old. You have a big plug and a small plug, and you have a big slot and a small slot. You can't turn this but one way. This is the high side, this is the incoming energy, this is the ground on this side. You have to turn them in the right direction, otherwise you can't get it to plug in. And most of the more modern houses have these in it. And they also have a third, and this is another ground. So this is a ground, but this is a backup ground. So if you get a surge, this will draw it off rather than all having to go through that. Okay? This is only a two-prong plug. I can't think of anything in this room that would have a three-prong plug, but for instance, our vacuum cleaner is a three-prong. I'm pretty sure. No, it's not. It's two, but it's oriented. But they call this a energized load carrier. This is the load carrier. That's the grounded or neutral wire. The three-prong plug that goes in there provides another grounding wire. Now, other devices are polarized plugs, and that's really what this is. I don't know why they didn't say it there. It only goes one direction. And then you have the others called ground fault interrupters. These will usually occur in your kitchens and or your bathrooms. I know we have some in our kitchen, and we have some in one bathroom. I don't think the other bathroom. No, both bathrooms have. They were adapted. They were added later. At our house in Georgia, every outside plug is a ground fault interrupt. In fact, the one in our house here, our exterior plug, the plug outside isn't, but the circuit breaker is. Okay, it has a ground fault interrupter at the circuit breaker. And what that does, that provides you yet another level of safety. Okay, if there ever was too big a surge that this wouldn't take care of, then it cuts the circuit. Okay, and if you have one of those plugs, usually in the kitchen or bathroom, that has the 2 or 3 little buttons across, one's a test button and the other's a reset button. If you get too much current, it'll pop it and the current goes up, the circuit goes off. Undo the things that cause the problem, press the reset, and it comes back on again. My younger brother hates those things. He overrides them, but I don't think that's a good idea. That's it for the chapter. All right. Any questions? Okay. Nothing replaces reading the chapter. I say it every chapter. I mean it every chapter. But once you've read it, maybe a time or two, then try your summary. And this is a pretty long summary in this one. It's almost a half a page on page 171 and more than a quarter of the page on page 172. So quite a bit of a summary there. A lot of words in italics, and a lot of those words in italics are going to show up in your key terms later. But there's also a summary of equations, and this chapter has probably more than most. I would definitely say 11 equations. Not bad things to put on your formula and equation sheet for your test, which will be Thursday. We will have a test on chapter 6 on Thursday. Okay? But then comes I think the best thing to study for your test. You're applying the concepts, and we have here 50 questions. That's probably 1 or 2 more than normal, and their answers provided. They're all multiple choice. Most, not all of your tests will be multiple choice. There'll be a few calculations, maybe 2 or 3 calculations. Yeah. And maybe a fill in the blank or 2. But most of them will be multiple choice. They won't be the same questions as these, but we are covering the same material. So if you know these, you're going to know those. So go through those. Questions for thought. This chapter surprisingly has a few fewer than normal, only 12. And for further analysis has maybe 1 or 2 more than normal, 7, whereas most of them have maybe a little bit less than that. And then the group A exercises. If you have a big book, I know those answers are in the back. I don't know if the small ones have that or not, but the group A exercises are pretty good to do too. And this has fewer than normal. I would have thought that it would have more, but it's still a good number. All right. Now, just like we skipped chapter 5, which is sound, we're also skipping chapter 7, which is light. We just don't have time for it. Wish we did, but because this is supposed to be physics and chemistry, and we've been hitting a little bit of chemistry along the way, but now we're getting ready to hit it a little bit harder, and that's chapter 8. Now, I wish we had time for chapter 9. That's really more fun to me than chapter 8, but you really need to know 8 in order to do 9. And by the way, though, any of these chapters we're skipping, if you find anything in there you want to write on, that's still a good paper topic. All right. By the way, when are papers due? Yeah, Tuesday is the last day that you won't lose points, but they're due any time. Get them to me today, get them to me tomorrow, get them to me Thursday, get them to me Friday, get them to me Monday. But the last day you can turn them in without losing points is Tuesday of next week. So try to do that. And for some reason, it's not opening 8. Let me try it again. Okay, we don't have a lot of time left, but let's see what we can get done in the little time we got left. We've got 11 minutes. Okay. From current slide. All right. Chapter 8 is atoms and periodic properties. Okay? Now, we're going to do this today. We're not going to get too far. And then we'll do it next time. Next time we don't have a lab, but we do have a test. So that means we got 4 hours of class. We may finish the chapter next time, may not, we'll see. We're not going to push it too hard, but we do. But we do have a test on chapter 6 next time. So at least 30 minutes will be reserved for the test. So the core concept here, and this is on your page 205, is different fields of study contributed to the development of a model of the atom. Pretty innocuous sounding core concept here. But we're going to talk about a whole range of things and people. The ancient Greeks, going back to the time of Democritus, who actually was probably 1 or 2 generations before Aristotle, maybe about Socrates' time or a little before him. He had this idea, and I think I've described this several times, that if you had a piece of iron here, say a long iron bar or something like that, and you broke it into 2, still you have iron. Break the smaller one into 2, still you have 2 pieces of iron. Break the smaller one into 2. Just keep breaking into 2 and 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 into 2 as far as you could. At some point, Democritus reasoned that there had to be some particle that was the smallest particle of iron you could have. Now, he did this just by thinking about it. He said it has to be this way. And he said the smallest particle would then be an atom, which comes from the Greek word for indivisible. Atom, indivisible. You can't get any smaller than that and still be iron. Okay? Now, after his time, Plato and Aristotle's time, there was Socrates, then Plato, then Aristotle, and some of them overlapped. In fact, all 3 of those overlapped some, but that was the age range. Socrates was the oldest, and Plato, and then Aristotle. They ignored Democritus, who had been 100 years before or something like that. Said, no. Matter is continuously and infinitely divisible. That you can't get any smallest piece. It's a continuum. It always is there. So that lasted from probably 200 BC until 1800 AD. So almost 2 millennia, everybody believed that. Okay? Or most of it. But then came a thing, and it was really Aristotle's fault. It was his fault. Another thing that he said, in addition to that it was infinitely divisible, it was a continuum, he also said there were only 4 elements. And we talked about this before too. Anyone remember those 4 elements? Earth, wind, water, and fire. Okay? 3 of those made a single group. Earth, wind, and fire. Okay, never mind. But the 4th was water. And he said those were the only 4 elements there were. Well, then about the 16 and 1700s or so, these Europeans who were really pretty clever and also very materialistic said, hey, if that's all there is, if that's the 4 elements, we can combine these. We can grind them, we can heat them, we can mix them, we can dissolve them, we can do whatever we want to them, but we can come up, because look at this. Earth materials are basically free, right? Wind is free, okay? Fire is not too expensive, and water is basically free. If that's all there is, the 4 elements, we can combine them in certain ways, and we can get gold, we can get platinum, we can get silver, we can make ourselves a mint off of this. As my mother-in-law said when we were shopping in Canada, I made a killing in there. Well, what she didn't realize, the exchange rate, they really killed her, but she didn't realize that. She thought she had bought so much for so little dollars. But, of course, the exchange rate is not great. Okay. So anyway, these alchemists was what they were called. They started trying to mix and mine and change and connect. And they were very creative in what they did. But they found out in a very short time they had to write really careful notes, because otherwise they'd wind up doing the same thing over and over again. Oh, I've already done that. So they were very careful about documenting what they did. And sure enough, they were able to purify some materials that they had never known they could purify before. And after a time, they came up with a list of what they called elements that were like 27 or something of them. Lavoisier put that together. He said, hey, here are the elements. It's more than earth, wind, and fire. Earth, wind, water, and fire. It's a lot more than that. Of course, they still had some of them wrong. They still were listing heat or caloric as an element. It wasn't. But anyway, they got it down, and then they started noticing in their careful notes that when they combined certain things together, they always went together in certain ratios of the masses. If you had 2 grams of hydrogen and 16 grams of, 8 grams of oxygen, you made 10 grams of water. I may have the numbers wrong. But always, that was what they called the law of definite proportions. If you had extra hydrogen and combined them, you still got 10 grams of water, but you had extra hydrogen left over. If you had extra oxygen, combine them, you still got 10 grams of water that had extra oxygen left over. So they only combined by definite proportions. Well, that led John Dalton in the early 1800s to come up with this model. And this went back to Democritus, that there were smallest particles there were, atoms, to explain the chemical reactions. And here's how he did it. He said, every chemical that we know about now, oxygen, carbon, nitrogen, all these, have a certain number of hooks on them. Now, he figured they weren't really hooks, but it was his model, what he used. And oxygen had 2 hooks, hydrogen had 1. So when you got oxygen with 2 hooks, there were 1 to a hydrogen here, 1 to a hydrogen there. All the hooks were filled up. You got H2O, water. And that's why they always combine that way. Methane was carbon and 4 hydrogens. 4 hooks around carbon, 1 on hydrogen. There you had methane. And then you could just build all these other. Carbon dioxide, 4 on carbon, 2 on oxygen, 2 oxygen with 2, 2 with 2, carbon dioxide. So he could form all these different things. That was his atomic theory, explaining chemical reactions. Now this picture over here, I don't know if you can see it from where you're sitting, but here's a nucleus. Now this is way bigger than any nucleus ever is. They've enlarged it so you can see some are protons and some are neutrons. And then around this is a cloud of very tiny particles called electrons. Now, there's a bunch of dots there. There's not that many electrons. It's just that the electrons could be located anywhere in that. So they put a lot of dots to show where they could be. Okay. And there's one series here, and there's another series out here. You can't see them well, not from where you're sitting, but they're in the book a little bit better than that. But that nucleus is way too big in size. In mass, it's enormous, but in size, it's incredibly tiny. The electrons are even tinier, but they have almost no mass at all. But they take up this huge volume. The nucleus takes up hardly any volume at all. The electrons basically are a cloud around the nucleus. A huge cloud, but not hardly any mass. All the mass is in this tiny, tiny, tiny little nucleus. So it's really dense, and everything around it, those electrons are almost nothing. They are something, but not much. So most of everything around it is empty space, as in outer space. Nothing. No material in there at all. So as my brother came home from his sophomore year of physics at Georgia Tech, and his physics professor had explained that, he said, most of everything is nothing. Okay, and in fact, that's really true. Okay? Now, we don't have much time left. I don't think there's time to get through this slide, is there? So we're going to start on page 206, right at the bottom of the right-hand column, this list of starts 2, and then on top of the next page 3. These are these 5 principles, you might say, of Dalton's atomic theory. So that's where we'll begin next time. Okay? Now, if you notice, this is a pretty long chapter, and we're going to run into tons of individuals in here. this will take up pretty close to maybe all of the next class. Maybe we'll finish, I don't know. If we do finish chapter 8 next time, that's Thursday, then we'll have the test on chapter 6. That's definitely going to happen. And then that means the next Tuesday, if we didn't finish chapter 8, then we'll finish chapter 8 on Tuesday. If we do finish chapter 8 on Thursdays, because all we've got is the test then what we'll do is on Tuesday of next week, we will have the lab for chapter 8, and then that's all we've really got. And then on Thursday, we'll have the test on chapter 8 and the final exam. Now, if any of you want to knock them both out on Tuesday, I'll try to have them ready. Okay? But that's not required. Certainly, if you have other finals and things like that you want to focus on, you can wait till Thursday. We'll see. We'll know Thursday how much we get done in chapter 8. If we finish it, then we'll have an option on next week. If we don't finish it, then we'll still have sort of the option, but we won't have as much time to operate those options. So we'll see what happens from here. We're in a pretty good shape, I think. And what we'll plan to do, if most people are going to be finishing up on Tuesday, let's plan to have pizza on Tuesday then. Okay? But if most people are going to plan to be here till Thursday, let's wait and have our pizza on Thursday. So we'll find out Thursday and we'll decide that for next week. Okay? Any questions? All right, then I'm going to... Good deal. Okay. Who wants to be aluminum? Oh, look who came in. Let me get you a lap. Here's Chris. All right, you didn't see any of the others, did you? All right. All right. Who wants to be copper? Okay, here's copper. Okay. Who wants to be iron? No iron men or women today, huh? Okay, iron. Okay. Who wants to be lead? You get the lead out, huh? Okay, who wants to be lead? Come on, I got up until 6. Huh? Okay. Okay, you're lead. Get the lead out here. Okay. Who wants to be nickel? Nickel? Come on. I'm here till
people now.
I'm here till 6. Who wants to be zinc? Tin. Tin man. Who wants to be tin? Okay. And how about zinc? Well, we're going to do this right now. Okay.
You want to do it now?
Okay. Now, I've left off the last few, and she appreciates your volunteering. Okay. I'll do something good for you later. Okay. So, what we have here is a number of magnets on this board here. You can either use this one or that, neither one, doesn't matter. I want you to bring your metal up there and see if it's magnetic or not. And you put yes if it sticks, no if it doesn't. So aluminum. Who's aluminum? Aluminum. Okay, yeah. So hold it against one of the magnets and see if it sticks. Either this side, that side, this side, or that side. No, on the side. On the side. No, here or here. Does it stick?
Nope.
Nope. Aluminum's a no. And I don't know, maybe the magnet's not working. We'll see. Okay. How about copper? Good conductor copper. Who's copper?
Does that see you?
Yes, it's you.
What you think?
No.
No. No on copper. Iron. Well, it's all rusted. I don't know. Will that work? I don't think so.
I don't know. Where are we putting it?
No.
No, on the side.
Right here. Right.
Is it here or there?
Oh,
calling us.
What'd you say? Oh, yes, iron did stick. Okay? So iron's a yes. Lead. What you think?
no.
No, no lead. Nickel. Bright shiny nickel. Who's nickel? All right. You got volunteers, I think, too.
Yes.
Oh, yes. Nickel sticks. Okay. How about tin? SN. Tin. The Tin Man. Okay. Hold on.
No.
No, tin doesn't stick. How about zinc?
It don't.
The last one, right? Side. Yeah. This or that. Okay. What you say? No, no on zinc. Okay. We didn't have a cobalt stick. I don't even know what it looked like. That would have stuck. None of the rest had a chance. Because why? Only iron, nickel, and cobalt are naturally occurring magnetic materials. These others, though they're good conductors or other things like that, they don't. Now I left off the plastic, wood, and styrofoam. Y'all know what that would have done. No, no. Okay, so give me your plate before you leave. Inner Y or N. Okay. And you don't need to put anything down for plastic, wood, or styrofoam. All right, now the next part, unfortunately, is going to take some trial and errors here. What I have is a whole series of pins. Some of them are through styrofoam, some of them are not. And what I want you to do is each of you take a pin out of here. Anyone will do. Okay. Okay. Take a pen. Okay, stick me with it here. Okay, I got you. She's getting back at me. Get a pen. Pen.
That's what you use to like hold
Okay,
it.
get a pen. Okay, now what I want you to do is this. I want all of us to stick them in the iron filings here. And see, mine came out pretty well coated, right? So I want each of you to do that, and then to get them off, brush them off in the iron filings. I don't want them all over the tabletop or the floor or something. Save them here. So everybody stick their pens in and see who comes up with the least number of iron filings. He's got too many. Who comes up with the least number? Okay, looks like most of you are getting too many, right? Who came up with very few? Anybody? Come on, everybody get them in there. Don't want them holding all day. Who came up with, oh, yours is pretty small, isn't it? Yes, I think we have a winner here. Okay? You just stick it in, right? All right, we have a winner. Okay.
I didn't do it.
The rest of you put your hands back. Wipe off your iron
I
filings.
didn't do it.
Well, do it. Okay.
Okay, what I put?
Well, we got one that came out almost clean, right? See, all of you get. See, I've used these pens so many times. So everybody, wipe off your iron. Not on the floor, in the bucket, in the pot. Okay. Put it back in here. Oh, yours is a logo. Okay, you hang on to that. Okay. Okay. Oh, you have little ones. Did you get yours white? Okay, good. You got a little one too. Everybody got their pens back? Oh, did you ever stick it in? Okay. Done and home to yours, look, right? Okay. Now, where we are is number B1. Test 1 to see, okay, several pins have been placed on 2 pieces of styrofoam. Test 1 to see if it's magnetized by testing the point. Oh, you didn't do that, did you? Do the head and do that too. You put the point down, right? Do the other end, head. Okay. Not much on that either, is there? Okay. Everybody saw that? A little bit stuck, but not very much. Okay. So the point and the head into the container of iron filings. If it's magnetized, hers was slightly, but not much. Place it in the, well, we're not going to do the water. And what we want to do is determine which is the, okay. No, if it is magnetized. Hers was not. Okay? So, what we're going to do, let's take one of the was magnetized, just for fun. So we go ahead and answer the right question. Okay, I'm going to test this one more time just to make sure. Yeah, it came up dirty, and the head also a lot more than hers did. Okay. Now, what we're going to do is, here is a compass, which is a little magnet. And I'm trying to get it to settle on north. Okay, there's north. I want someone to take this and hold it, either the point or the head, near the north seeking pole of the compass. And see what it does. Just hold it close to it. Okay. Ooh, what's it doing to it? Okay, but which way? Yeah, come from the side. Yeah. It seems to be pushing it away, doesn't it? Okay. Do it to the south seeking pole. What's it doing? It's attracting it. So what must be the point of that pin? North or south? Second? It's repelled the north and attracted the south. What do the poles do? Like poles repel, unlike poles attract. So the point was north. And isn't that what it asked me? And which is the south seeking? Did you try that?
So the point was north.
The point was north. Try the head and see what happens. You have it, don't you? Okay. The point must have been the north seeking was which? The point, because it repelled the north and attracted the south. Now do the head and see what happens. Sort of come at it from the side. Ooh, what's it doing to the south? Repelling it. Okay, hold it near the north. It's attracting the north. So what must be the head? The south seeking. Okay? So that's number 1, B1. Okay, I'll take your pen, put it back in. Thank you. All right, the unmagnetizing or weakly magnetizing. What we want you to do is take it over here to one of those magnets, the ones you held up to before, okay, and take the point and stroke it along in one direction on the side of one of those magnets. Okay, okay, stroke it, yeah. Okay, she stroked it a few times, okay. Now what she's going to do and see if that changed the magnetism in it. Oh my goodness, yes. She came up completely clean last time. Look what she got this time. Okay, very good. Okay. It did get magnetized. Okay, now, did you stroke the point or the head? the point. Now the head wasn't magnetized before either, was it? Flip it over and put the head in and see if it got magnetized. It shouldn't, should it? Oh, look at that. How did you do that? Okay, wipe it off. Okay. Any ideas? Did it get magnetized? Yes. Explain how you increase the magnetism of the head when you stroke the point. Okay, that is sort of a true statement. It is a good conductor, but the more important thing is magnets are always Say again? Okay, where are we going? All right. Okay. Magnets are always dipoles. You can never have an isolated North Pole or South Pole. So if you make one end of a magnet magnetized, no matter how far away the other end is, it's going to be equally magnetized. Magnets are always dipoles. Always. Okay. You cannot have a magnetic monopole. Okay. Now, using the compass here, not the other one, but the compass here, someone get her pen and see which end of it is north-seeking and which is south-seeking. Okay, he's got the point, he's holding, oh, what's it doing? What's the point doing? It's attracting the North Pole, so it must be a what?
So the point is north.
No, it attracted the North Pole, didn't it?
Oh, so it's a south.
Yeah, look at that. Pulled it right on over there. So, okay, try the other one. Whoa, it attracted the south. So which of these is the north-seeking, the head or the point? Is which? Yes, the head is north-seeking because it attracted the south-seeking pole, and the point is south-seeking because it attracted the north-seeking pole. Got it? All right. Now, what we're going to do, we've got 2, 4, 6, 8, 9. Okay. We're going to go downstairs to the records office. Okay? Because I don't think they have any filing cabinets in here. So let's go down to it says here room 265, but it doesn't have a file cabinet anymore. They don't have any here. So let's go downstairs. Bring your paper. We'll be coming back here in just a few minutes. I can turn off the lights and close the doors. But if you want to carry stuff, you can. Okay. Whoa. Okay. Oh. I hope the charge will keep well enough. Move this. And pen. Okay. My computer. Okay. Okay, we'll go this way. Okay. Hey. Take a right past the restrooms. Okay. And we can either go right or left, I don't care. Just all go the same direction. All right, thank you. Okay. We'll take a right in the records office, registrar's office. 2, 3, 4, 5, 6, 7, 8, 9. Take a right here. Okay, let me get in the lead here. All right. Let me get in front so I can guide you through. Okay, follow me. We're coming on here. Okay. We're going back here for just a minute. Okay. Hey. Howdy. Good. We're going to invade your space for a little while, but you're welcome to stay. You're welcome to stay. Okay. Now, who wants to be my compass operator? Okay. Is there a plug nearby?
There's one under that table,
Okay.
and the other one I think is over got a copy.
This will do.
Sorry. Oh man, I can't get up.
I made it. Okay. All right. Now, what we have here are some metal filing cabinets. You can take any one you want to. This one be okay for you? Okay. Now, okay, hold on. Okay. What you're going to do is take the compass. This is a B5, a 2B5. Take a compass to here and go to the metal file cabinet in the room, one of them. Hold the compass beside the filing cabinet near the top. Okay? Near the top. Now, what you notice? Move it around some, this way and that. Okay, move it over here some. Oh, wait a minute. Okay, back that way. Okay. What happens? The south-seeking pole of the compass is attracted to the top of the filing cabinet. That's strange. Is that maybe just because it's metal? Well, why wouldn't the north-seeking? Okay. I'll do this. Oops, no, north-seeking won't be attracted to it. So it must not be just because it's metal. So this must be sort of like a magnet itself, right? So, what happens to the compass needle? The south-seeking pole of the compass is attracted to the top of the filing cabinet. Okay? And number 6 is why. Filing cabinet must be magnetized. Filing cabinet must be magnetized. Now, did one of you sit down here and stroke this with a magnet while we weren't looking? No. Did any of you do that? Like Brandis did with the pen? No. No one has. Okay? So why would that be magnetized? Well, do you remember my story in class of nailing the nail into the post over my head, and then the nail popped out, and I looked around for it, and it was attracted to the hammer? Okay? Whenever you perturb a magnetizable material, like iron, like steel, okay, and in the presence of a magnetic field, it becomes magnetized. And what I bet you people have been doing is opening and closing these drawers over time, right? And every time you do that, you're shaking it up. But where's the magnetic field here? The Earth's magnetic field. Same thing this compass points to. This compass points to north. Okay? Because of the Earth's magnetic field. Okay. Now, because number 6, anytime that you're opening and closing or perturbing or disturbing magnetizable material in the presence of a magnetic field, it's going to become magnetized. Now, somebody else, the same person, want to hold this near the bottom part of the file cabinet. Anybody? I'm here till 6. Okay. Seth is willing.
What you said for the top part?
let's come to this end of it, okay? We may have been wrong there. I think what was happening there, yeah, now we got it. Near the top, let's go back and change what you had. Near the top, the north magnetic pole is being attracted to the top of the filing cabinet. North magnetic pole to the top. That's number 5. Same reason though. Okay. Now hold this near the bottom, and what do you see? The south magnetic pole is pointing to the bottom. Wait a minute. Why would that be the case? Why would the south end of that attract the bottom end attract the south pole, but the top end attract the north pole? Okay. Number 7, hold the compass beside the file cabinet near the bottom. What happens with the compass needle now? The south pole was attracted to the bottom of the thing. Okay, now, this is printed 2 sides. So, which is the north-seeking pole of the filing cabinet, the top or the bottom? Wait a minute. What was it pointing to here? North. North doesn't attract north. The north-seeking pole must be the bottom, because that attracts the south-seeking pole of the compass. Okay? Okay, we're not going to do number 9. I've tried it here. I can't do it. It worked at home. I can't do it here. Okay? Now, but 9 or 10. 11 we can do. Explain how this made a magnet, even though, and we've already answered part of it, but the other part is why is the bottom north-seeking and the top south-seeking. Now, here's what we'll think of here. Would someone point, to your best guess, toward the North Pole? You can even hold the compass if you want to. Point toward the North Pole. Okay, I see someone pointing it this way, right? That seems to be about where the compass needle is, right? Except I'm pointing out into space. Okay, up I'm pointing even more out into space. We live on a globe. And we're here, the North Pole is somewhere down there. Down there, you know. And that's where the field lines are. See, if I held, it's sort of stuck hung up if I did this. So the field lines are there. So therefore, the bottom part of the cabinet is north-seeking. The top part is south-seeking. Because the field lines on the Earth go like this. There's North Pole somewhere down there. South Pole is on the other side, and if we're on the other side of the equator, it would be pointing that way. Okay? So because the Earth is a sphere, the North Pole is a downward component, not just a horizontal component, a vertical component. And the bottom of the cabinet is closer to the North Pole than the top is. So therefore, it's the North Pole. And guess what? Magnets are always dipoles. You got it. You said that. Okay, good. Excellent. Excellent. Okay. Let's go back to the lab. See if I can get out of here. All right. Thank you for your time and sorry for the interruption. It was all in the name of science. Okay.
I learned
Okay.
something there.
Okay. Anyone cell phone?
It's mine.
It's right. Okay, good. Okay. We've been spying on your records here. Okay, I'll meet you upstairs. I'm too lazy to follow you guys. Okay. Okay. Everybody back? Are we losing people? Oh, okay. Should have 8 left. 2, 4, 6, 8, 9. Okay. I think we're still recording. Yeah. Okay. So, explain how you made a magnet without affecting another magnet. The vibrations or perturbations of the drawers in the presence of the Earth's magnetic field made it a magnet, and the field line pointed with a downward component, which made the bottom north. Okay, now we're going to use our Toyota Technical Education Program Electromagnetic Master. Okay, this is for the C part. Okay, I'm currently plugged into station A. Red to red, black to black. Okay? Now, what we're going to do, if I can get this to work, here's one problem being in the old electronics lab. There's a lot of magnetic materials around here, so I'm having trouble getting my compass to behave. So I think that's pointing north now. Okay? So I'm going to set it right here. That may not work well. I may have to change the board a little bit. Okay. So what we're going to do is station A, and I'll plug the black wire into black and the red into red here and there. Okay? Go and place a compass near the coil. Here's the coil we're dealing with, A. Everybody stand up so you can see what I'm talking about. Okay? Here's the coil A. And there's my setup here. Okay? Now, and what I'm going to do, I'm going to set this for 1.5. It may not work, so I may have to crank it up some because of the magnetic field. But when I do this, when I touch what I'm going to do is plug and unplug. Okay? So I'm going to unplug it now and turn this on and set this for 1.5 or somewhere around there. Okay, it's 1.6. Okay, when I plug it in, see if you see the compass needle bulging. And these old wires, okay, in? Did it move at all? Okay. Oh, I think I've got Michaela's drifting. Okay, we'll crank it up some. Yeah. See if it moves out. In? No. In? Okay. In? Okay, not moving at all. Okay. Let me check my other wiring here and make sure these are all in good. They seem to be. Okay, we'll crank it up some more. Okay. It may be that it's too close to where it needs to be anyway. Wow, why is that drifting like this? Goodness gracious. I think it's feeling some of these magnets here. So let's see what happens here, if anything happens. Ah! You see? Mm-hmm. All right. What happened? Right. The north-seeking pole swung around and pointed to the left end of the coil. What happens to the compass needle? The north pole swung around to point to the left end of the coil. I bet you I could turn it down some. This is C1. What happens to the compass needle? The north seeking pole swung around pointed to the left end of the coil. So which would have been the north pole of the coil? Left or right? Second? Right, because it was seeking the south end. You're absolutely correct to say right. Now, what I'm going to do is switch batteries. Switch orientation. Okay? Now I'm going to plug the red into black and see what happens. Okay? Now again, we're pointing right there. So let's move it up here. See? There's a strong magnetic field somewhere in here that's reorienting that. Let's see what happens if I do this. Okay, maybe I have to crank it up some more. Yeah, this is drifting. Sorry. Whatever it is there, maybe it's the spigot here. Oh, I'm wondering what's going on here. This thing's got to turn too. Okay, let's try it again. Ah, what happened? The south-seeking end points toward the left end of the coil. So are there any changes? Yes. If you change the direction of current, and this is DC current, you change the polarity of the, basically that's the solenoid. Acts like a solenoid. All right. Now we're going to move to station B. Okay, I don't think we need the compass anymore. Okay. Now at station B, we're going to plug the wires according to the colors. So let me reverse these again. Okay. And we're going to move yellows to yellows. All right. Now we got multiple things are going to be going on now. Okay. I'm going to need one person at the lights.
Are those yellows supposed to be at station B?
Okay. I'm sorry, B, you're right. We would have been wondering why that didn't work. Okay. Turn them all off but one bank. Okay. All right. Now, when I tell you we're going to turn them off, but I got to make my other assignments first. Okay, we're going to crank this up to 9 volts. That may not be enough, but we'll see if it is. May have to go higher. Unplug it for now. Whoa! See, the thing is, with it plugged in, plugged out, it changes the voltage big time because there's a lot of resistance somewhere in this system. So we may have to go back. So I'm going to leave it right there for now. Okay. 9-volt battery, red to red, black to black. Okay. Now, what I want one person to do, when I do the touching and connect and disconnect. Now I'm going to yell them out both times. Connect, disconnect. Somebody look at these lights. There's a green and a red. Some other person look at the ammeter, the micro ammeter, and it's either going to go right, left, or both, or whatever. Okay? Now we may have to do some adjusting at first. So who's going to look at the lights? Okay. Who's going to look at the ammeter? Okay, you're going to do ammeter, she's going to do lights. Can you see the lights well from where you are? Yeah. Okay. So what I'm going to do is connect and disconnect, but go on and turn off the light. Okay? Wait. Okay. Turn it on again. Okay. Now, I got it. Turn it off. Connect. Disconnect. Any lights? Any ammeter?
I'm supposed to see the ammeter in the dark.
Okay. Okay, that's it. Yeah. First, we're only going to do lights because you can't see the ammeter in the dark. Okay? Then we'll do it with the lights on. So, No, okay, we'll start with the lights. So turn the light off. Turn it off. And on the light. Connect. Okay, turn it back on. Okay. All right. Turn it off. Okay. Connect. Disconnect. Any light come on?
It was a spark.
Which one?
Disconnect on the left side.
Disconnect on which one? Red or green?
I ain't really see no color. But
Okay.
it's green.
Give me on the color. Give me the lights again. Just a moment. Okay. All right. Turn them off. Connect. Disconnect. Anything? Green came on what?
It blinked when you disconnected.
Disconnect. Okay, we're going to turn it up just a little bit. See if we can get the red light to come on. Okay, turn on the light for just a second. Okay. Now, turn it off. Connect. Disconnect.
Same thing.
Okay, still no red, huh? I'm going to crank it up a little bit more. Okay, turn it on again. Okay, turn it off. Connect. Disconnect.
It was red when you connected it.
Okay, red connect, green disconnect. Okay, turn the lights on. All right. Now we'll do the ammeter. Okay, see if you can see it move. Connect. Did it move?
It like wobbled a little bit,
Which way?
like in the middle, like to the left,
To the left? Disconnect.
to the left,
Left. Let's do connect again. Connect.
right.
Right. Disconnect. Left. Right. Okay. Y'all got it? On connection, the ammeter went right, which is positive. On disconnect, it went left, which is negative. Okay? Okay, did y'all get that? Record what happens to the light and ammeter. Light, red on at connect, green on at disconnect. No, wait, I'm sorry. Number 4 is just connect. So what happens to the light? Red on at connect. And what happened to the ammeter? Ammeter went to the right on connect. Positive on connect. Got it? Okay, I'll say it one more time. Number 4 is only asking about what happens on connection. According to what happens to the light on connection, red light came on, ammeter went positive. That's all you have to put for number 4. Got it? Okay. All right. When disconnected, what do the lights and ammeter do?
Green and disconnect.
Green on disconnect, and ammeter went negative. Right. Okay? And that was at 13 volts. Okay, now what I'm going to do now is switch poles. Put the black in the red, and red in the black. So you ready on the light? One more. You looking at the light? Connect. Anything?
A green spark.
Okay. Disconnect.
Red spark.
Red spark. Okay. Hang on to that thought. Turn on the lights now. Okay. Look at the ammeter. Connect. Left. Disconnect. Right. And just barely. Okay. Y'all want to write that down? While I get up. Yuck. Okay, this is number 6. Hold the red on the negative electrode and black on the positive. What happens to the lights in ammeter? On connection, which came on?
Green.
Green came on? No, red came on connection. Yeah, red came on connection and the ammeter went negative. Okay? Red went on connection and ammeter went negative.
Yes, this is number 7.
Okay? Turn the page to number 7. When we disconnected the circuit, which light came on? Green. And what happened to the ammeter? Positive. So green light, positive on disconnect. Now, explain the observations. Okay, let me explain to you what's going on here. These lights are what we call diodes. A diode only activates when the current is moving in one direction. The green is when it's moving one way, the red when the other. That's why they both wouldn't come on at the same time. And we saw that the green came on when it was a positive current, right? And the red came on when it was negative. When I switched the poles, just the reverse happened, but still, reverse happened on both of them. So still the red came on with negative and the green. So the current was moving in one direction. Now, why was that happening? We were sending the current through this coil here, right? And anytime, I want you to notice it. When it's plugged in permanently, if I can plug it in, there's no change of anything. No lights on, nothing. It's only on connecting and disconnecting that you get any change at all. And then it's very slight. The reason is, it's only when there's a changing, you see, this is sending current through here. This is changing a magnetic field in here. What this is doing is sending current here, and it only happens when there's a changing magnetic field. On connection, it's increasing. On disconnecting, it's decreasing. Unless you switch the wires, and then it's reversed. So this is only picking up a current when there's a changing magnetic field. That's the key. Only is creating a small, really small current when there's a changing magnetic field. Changing magnetic field here induces a current there. Okay, we're going to move down to 4 and 5. Okay, or C. Thank you. Okay, I'm going to switch these back. Now, we were at 13. Oh, I got to move the yellows too. So now we're at station C. So this is question number 9. At station C, place the colored wires in the corresponding plugs, moving the yellow wires from 2 to 4, and place the red wire in the positive. And now it says a 1.5 volt battery. It may not work at 1.5, but I'm going to crank it down there to see if it will. Much lower than what we had before. Okay, I'm going to stop there. It's 1.6. Doubt if it's going to work, but we'll try. Okay? Now, I need you on the light. I need the light looker. And then when we turn the lights back on, the ammeter looker. Okay? When you're ready, turn off the light. Connect. Anything? No. Disconnect. Nothing? We'll turn it, crank it up some. Okay, turn on the light for a moment. Okay. Okay, turn it off. Connect. Disconnect.
When it was connected, the red and the green came on. Disconnected, it was just green.
Okay, turn it on, light on again. What is happening is it's wobbling here. Okay, turn it off. Connect. Disconnect.
Same thing happened.
What happened?
The green was disconnected and the green and the red was connected.
Okay, turn on the light one more time. Okay, and try it again. I'm doing some, okay. Turn it off. Connect. Disconnect.
Same thing.
Okay. If y'all could see what I'm seeing here, it's arcing and sparking when I get close, so it's connecting and disconnecting real close, and that's why it's flickering. But it's only red on disconnect, because that time, then I'm pulling it straight out. Okay?
It's only red on connect.
Oh, red on connect?
Yeah, I said red and green on connect, and then just green on disconnect.
Yeah, green on disconnect. Okay. Turn on the lights one more time. Okay. And we're at 3.4 volts, by the way. Okay. Notice that. We were at 13 before, we're at 3 here. Okay. Now, the red and green is on disconnect, and let's just say red on connect, which is kind of backwards from before, but it's okay. So, this is number 9. Okay, and this is both connecting and disconnecting, so we put them both. On number 9, what was the light on connecting?
Red and green.
Okay, red and green. Okay, and disconnecting green only?
Yes.
Okay. Oh, did we do the ammeter?
No.
Okay. Look at the ammeter, we'll do that. Connect and disconnect. Okay, ready? Connect. Disconnect. Okay. Stronger or weaker than before? Stronger, but we had less voltage. We'll get to that later. Okay. We created more current, but not from here. Okay. So did everybody get that? Responses to the light.
It's going on too.
This is all on 9. This is connect and disconnect. Oh, here you go. Knock in from over. Have you been there
Also
long?
connect was what
What we're on page,
Connect was
page on there, number, we're on number 9. Okay. You probably don't need to see it. Okay. Okay. Number 9. Oh, you need it. Okay.
No, me. I did it wrong. Green only. That's what I got.
You just said red.
She said it. She said it back.
She said red on this head. That's wrong.
She said red on this.
I'm just on what you said, Dominique.
On the other page, it was that way, but on this one, it's red. It's green on disconnect. Can't really tell you why, but okay. Are we losing you? No, you left the thing. Okay. Thought we lost you. Okay. You can catch up later. Let's get back to this one. Or where we are? Yeah. You can pick up the rest of it. Okay. Did you get number 9 though? Is the question. Oh wait, we just did 9.
I got it.
Okay, yeah. We're going to get 9.
I'll get from her. I've already done that.
Yeah, but you need to for 10 then, because we're going. Yeah. Okay. All right. I'm going to switch wires, put black on red and red on black. Okay? Or I will. Now, let's first do the lights, and then we'll do the, you are looking at these lights, right?
Yeah.
Okay, good. Okay, turn off, wait. Turn off the light. Connect. Disconnect.
Connect is green. Disconnect is red.
Okay. Let's turn on the light. This is suspicious here. Let's do this again. Okay, I put the light, this is back on 9. Okay, turn off the light. Connect. Disconnect.
Same thing we got.
Same thing.
Yes.
Okay, turn on the light. So you're getting the same thing.
Like with the red and green, connect and disconnect was green only.
Okay, now let's do this one. This is switching the thing. This is 10 now. Turn it off the light. Connect. Disconnect.
Okay, both red and green on connect and just red on disconnect.
Red on disconnect. Okay. Turn on the light. Okay. Now let's do the ammeter. Watching. Connect. Second. Left, which is negative. Disconnect. Whoa! And that was a lot more than we had before, wasn't it? Okay. I didn't know there was that much more. Only 3 volts. Okay. Now this is number 10. Switch the wires on the opposite ends of the battery. Record the responses on connecting and disconnect. What was the lights on connecting and disconnect?
Red and green.
Second.
Red and green.
Red and green on connect. That's probably because of my wobble. And what on disconnect?
Red on.
Red only on disconnect. Okay? What about the ammeter? Connecting. Second. Negative. And disconnecting. Positive. Okay. Now here is the big question. And I think you need to come over here and see the board to get the answer for it. Okay? The question is, why on this one did we get much bigger ammeter readings on connection and disconnect, even though we're only at 3 volts here? Now here's what the situation is. We're connected, we're sending a current through here, and we connect, and this is what we answered on this one. Here we set the current through this end. We set the current through here, and only on connecting and disconnecting do we get light flashing and current change. Only when you left it plugged in, nothing happens. Disconnected, nothing happens. But when you connected or disconnected, you got a wobble. Here is very, very weak at 13 volts input. This was very strong at 3 volts input. Okay? Why was the difference? This is number 11, even though we had 13 volts here and only 3 volts here. Why was it? Second?
There's more wire over
Okay, you're close.
like the magnetic field, something to do with that.
Okay, it certainly is. Where is this? This is inside the oven. So more field lines are being cut by this than here. Here it's only on the end. You're only cutting the end field lines. Here it's interior, so there's a lot more field lines, magnetic field lines being cut, and it's only the changing magnetic field that induces the current in this. When it's constant, no current. Only when it's changing. That's why it's only on connect and disconnect, but there were way more field lines being cut because this one was inside. Okay? So that's why, even though this had the weaker battery, so to speak, 3 volts as opposed to 13 volts here. We had to crank it up to 13 volts just to get the lights, so you could see. And the ammeter just barely moved. Here, it moved big time. Look at the ammeter here. Connect, disconnect. You see when I connect, after I connect, it really goes right back to 0. It's only on connection and disconnecting that it moves. And it moves way more than it did on 13 volts here. Okay, and that's the reason. More field lines are being cut. Okay. Now, what I'm going to do now is move the yellows to number 8. What we're still going to look at is the microammeter. Okay? Now I'm going to turn. Now in this case, everybody see it? Can everybody see the board here? You got the north magnet on top, south on the bottom. It's hard to see, but that's the south. So the field lines are going that way. It always goes away from the north pole toward the south pole. Pretty much constant, okay, field lines. And what I'm going to do is turn this coil. And right now it's cutting a lot of those field lines. Now it's cutting less. Now it's cutting more, less, more, less, more, less. Okay? But as I turn this, I want you to tell me what the microammeter is doing. So y'all looking at the microammeter? Going positive. Not very strongly, but it is going positive. Okay? If I turn it the other way, well, wait, y'all answer that. That was number F, number 12. Plug 2 sets of yellow wires in the terminals 8 to terminal 14. One person should turn the coil clockwise, which is what I was doing. The others read the ammeter. And that was slightly positive. Okay? Ammeter went slightly positive. Got it? Okay? Would it help to have more lights on, or are you okay with the lights? Okay. All right, now I'm going to turn it counterclockwise. And y'all look at the ammeter. It goes slightly negative. Okay?
You said that was positive.
Second?
You said that was positive.
Negative is this way, positive.
Which way it went the first time.
All right, okay, let's look at the first time. Isn't that going slightly positive?
Now it's going positive.
Okay, and this way it's going slightly negative. Right. Okay. Now we're going to reverse the wires. And this time I'm going to go clockwise. Negative. Counterclockwise. Positive. Okay. Now, you didn't have to write those down for 14. Because 14 says, what type of connection does this have? Can anyone see this from where you are? You might want to turn on more light. There is a gap in the thing, and there's another gap on this end. Otherwise, these two, we'll call them brushes, are touching the copper there, and as long as they touch, it's going one direction. But as soon as it goes to go negative, they flip. Anyone know what that's called?
Series.
Say again?
Series.
Okay, kind of like it's creating something in series, but this is called a, you see this ring has a split in it, top and bottom. So it's called a split ring commutator. It commutes well, you weren't in class. The rest of you were, and you didn't get it, okay? Okay, the split ring commutator commutes, meaning it changes the direction of the current. So for half the turn, when the field lines are increasing and being cut, that creates a positive current. And then when it starts decreasing, it would create a negative current, except that the brushes flip their direction so it goes positive again. That's a commutator. That used to be what happened in your cars when you were charging your battery with your generator. Your generator is producing AC current, okay? But you can't charge your battery with AC because that charge, discharge, charge, discharge. So it used to have a split ring commutator that then every half turn it would flip. So whereas you got AC would be like this, half time positive, half negative. But with a split ring commutator, right when it goes to go negative, it flips it and it goes positive again, and flips it. And that's why it's a little bit of a pulse there too, because it's a pulsed DC current circuit. So what is the result of this? What I just said, a pulsed DC current, direct current. Okay, so the little answer to A in the thing was the split ring commutator. I didn't leave you enough room for that. And the bigger answer, what is the result of that? A pulsed DC current. Pulsed direct current, that would be the way. Okay. Now, all right, now I'm going to go to G. Okay, I'm going to plug yellow to yellow and yellow to yellow, putting on the same ones here. Now this time, notice what we've got. In this one we had a fixed magnetic field with a turning coil. In this one we have fixed coils with a turning magnet. Okay? And we're going to see what happens here. So someone pay attention to the microammeter. This is number 15. At station G, that one, we connected them like we said, and turn the magnet inside the coils. And you pay attention to the ammeter. What's it doing? It's doing what? Both ways. Absolutely both ways. Why do you reckon this is? Yeah, it's producing an AC current. Now what's happening here, you're changing field lines in here by flipping the magnet. That's what you're doing. And that's creating an electric current. We have a little AC generator here. Over here we had a DC generator. Okay? Now, why was this producing AC and this DC? What did this one have? That one did not have. The second? Yeah, numbers. Oh yeah, I'm sorry. Record the responses of the ammeter. 15 was the ammeter with both positive and negative. Okay? And number 16, what differences do you see from those of station F? Number 1, well, the main thing, At station F, you had DC, a pulsed DC current. At station G, you had an AC current. And the question is why? I think someone was about to answer that question.
The split ring.
Yeah, no split ring commutator at G. So it's strictly AC. F would have been AC if you could have, well, you'd have had to wire it differently too. But with the split ring commutator, it made a pulsed DC current. Any questions? How did you find the layout? What's that? Was it helpful or not? Was the lab helpful or not?
Yeah.
Okay. Good deal. Okay.
That was from the other answer.
Oh, okay, good. All right. Before we lose everybody, let me go over, because I know some people have just come in, what the deal is. I'm going to get close to my computer so I can record it again. Good deal. Thank you. Okay. So, where we are. Okay, everybody listening? Okay. Where we are, we finished chapter 6 today, electricity and magnetism. This is the last lab in that chapter. Okay. Now we're heading toward, and we started in chapter 8. We didn't get very far in 8. So on Thursday, we're going to have for the first, if it takes it, 4 hours, up to 4 hours, we're going to be in chapter 8. The odds are, I think we'll finish chapter 8 within 4 hours. Okay? Not sure about that, but if we we will finish chapter 8 in 4 hours. When we finish chapter 8, we'll stop and have the test in chapter 6. Everybody understand that? Okay, also I'm saying this largely for you. You got it? Okay. Test in chapter 6. Okay? Then, that would leave us, if we did finish chapter 8 on Thursday, and have the test on chapter 6 on Thursday, that's going to leave us for next week in Tuesday. Tuesday is the last day of class. Okay? So on Tuesday, I'm returning every lab and every test. That means if you haven't turned in a lab or finished the test by Tuesday, that's going to be a 0 on that one. Okay? So please get all of the things in today, tomorrow, Thursday, Friday, Monday, or Tuesday. Get everything finished and into me this week, by Tuesday, because I'm returning everything to you on Tuesday. Now, remember, I cannot return your research papers because they periodically ask for samples of student writing. So that won't be coming back. Everything else will. Also, your research papers are due by Tuesday. So if you can get them to me today, tomorrow, Thursday, Friday, Monday, or Tuesday, but they're due no later than Tuesday. After Tuesday, they start losing points. Okay? You can turn them in later, but you can't turn in the lab later. You can't do a test later. You've got to have those finished by Tuesday. Okay, so Tuesday we'll do the lab for chapter 8. If we didn't finish chapter 8, which I think we will, then we'll finish chapter 8 and then do this lab. Now, after that, it'll be up to you. And we'll talk about this on Thursday, day after tomorrow, okay? We'll talk about it whether most of you are going to think you might try to do the chapter 8 test on Tuesday or wait till Thursday and the final Tuesday or wait till Thursday. I'm going to give you all the options. If most people or even a few people are going to try to finish on Tuesday, then we'll probably have pizza on Tuesday. If most people are going to come back on Thursday, we'll wait and have pizza on Thursday. Okay? Sounds good? Okay. And if anyone who wants to wait, whether we have pizza Tuesday or Thursday, your final is scheduled for Thursday. And chapter 8 test, you can wait till Thursday on that too. So it's up to you whether you do it earlier or later. Okay? We'll talk about the rest of it next time. So we'll see you on Thursday.
Do we have a chapter 5 test?
Chapter 5 test?
Do we have one?
No, there is no chapter 5
Okay,
test.
I thought I was tripping. Alright, so can I take the 1 and 2 right quick?
The what?
1 test, 1 and 2.
Yeah, if you want to, you certainly can. Okay, is this my lab? There was a lab. There's a lab sitting here.
How many tests have we taken? Have we taken 4?
What's that again?
Have we taken 4 tests or 5?
We've taken
4?
4 so far.
4?
The chapter 6 test will be 5. The chapter 8 test will be 6. And then
the
will be the final.
Okay. Did you get my lab?
I don't know. What about it? Yeah, it's on top. There you go. That was easy. Okay. All right. Are there any questions? Okay, where did he go?